Welcome to HC18. The afternoon tutorial. Wireless in the home. Challenges and opportunities.
Jan doesn't need a long introduction. Probably you already know a lot about him. If you've recently taken a VLSI class, you probably use his book. And speaking from experience, it's much better if you take the class with him. So Jan is a professor at UC Berkeley. He's also the co-director and I think co-founder of BWRC and the director of GSRC, the Gigascale Consortium. He's been involved with research on VLSI and wireless for a long time now. He's held various appointments also at other places like IMEC and a few other universities, a visiting professor. And he got his PhD from the Catholic University of Leuven in Belgium. So with that, I would like to welcome Jan Rabaey.
Good afternoon, and welcome to this afternoon tutorial. I'm glad to be back here at Hot Chips. I think it's about 6 years ago, the year 2000, I gave a tutorial here on architecture for wireless. And actually, before I made these slides up, I kind of briefly glanced to the slides at that point in time. I said, hey, gee, let's figure out how much I was on track and how much has happened since then. And it turns out actually that things actually progressed quite nicely along what I projected at that point in time. So it's always good to look back occasionally and think about, hey, I'm basically projecting something forward, how much it really happened. So what we're going to talk about today is a very different topic. It's a topic that I think is of uttermost importance in the wireless space. It's basically wireless in the home. And what I'm going to try to do today is a couple of things. First of all, I'm going to try to show you that the home is an ideal incubator for a lot of the wireless technologies and will play a giant role in the wireless industry in the years to come. It probably, more than anything else, will become one of those next kind of, I would say, incubators of new technology. So what we're going to do is talk, first of all, about the home and the challenges to start. What are the potentials, what are the challenges, what are the problems we have to address. And then we're going to walk through a set of technologies that either have emerged or are emerging in the wireless space for the home, both in the high data rate and the low data rate type of perspective. And then to finalize the tutorial, we'll talk about how to bring this all together because as you know, it's very easy to develop new technologies and throw them around and things like that. I can make a whole bunch of different wireless links and so on and so forth, but really trying to tie them together in a meaningful application that's useful is a lot harder. And I think it's worthwhile to think that through a little bit and to maybe change the paradigm a little bit. Think about how we can integrate various technologies together in a seamless fashion in such a way that the user experience gets a lot better. So that's really where this tutorial will end. So, before I'll start the tutorial, there's a lot of material. We have about three hours of material, so it's not all coming from me. I really would like to express or acknowledge the contribution of a number of people, and I just have a subset here who helped me to put the slides together. So I definitely appreciate their help in that perspective. And one more thing, as Christos mentioned, one of the jobs I basically have, or one of the functions I hold, is director of the Berkeley Wireless Research Center. And a lot of the ideas that I will discuss today actually have come out of the center. Just a couple of words about the center. It's something we started about 7 years ago right now. It's 1999, where we basically set up a consortium between the University of California, Berkeley, and a number of faculty there, and a set of companies. Mostly semiconductor companies, but also companies involved in the service industry, wireless services, utilities, as well as the service side, like basically design automation, design services, and so on and so forth. We started with about 6, 7 companies. Initially, today, we have about 22 members in the center, all actually contributing on developing this technology we're talking about. And the goal of the center is really to look at beyond state-of-the-art wireless. What are the new trends that are emerging? Or given technology scaling, or assuming that technology scaling goes forward, what will be enabled in the wireless space? That's really the focus of the center at large. We have about 60 graduate students there, about 11 faculty, and it's been actually, I think, a very interesting source of innovation, bringing those companies, students, faculty, and so on and so forth together, and government in a advanced setting. Okay, that's kind of the introduction. Let's think a little bit about what we're going to talk about today. So when people talk about wireless, the first thing you always think about is cell phones, right? It's a good market. We're talking about 800 million to 1 billion handsets being produced per year, which is quite staggering in terms of number of chips. Companies like TI ship out about, I think, 2 million chips a day for basically wireless mobile components. So it's a really staggering big market. And you think about base stations, you think about large antennas, you think about coverage, and so on and so forth. And definitely an interesting area, definitely an area that has driven the semiconductor industry quite extensively over the last couple of years. But this is not what this tutorial is going to be all about. Actually, interesting area, but not what I'm going to talk about today. Instead, I would like to look at another perspective, what really could provide another jump in terms of numbers of components, number of chips needed. It's really this idea that comes with ubiquitous multimedia networking, and I'll come back to that in a second. So what we see is that over the last couple of years, we've seen something very interesting happening. We've seen this where in the past, you think about computing elements, big boxes, and so on and so forth. But scaling of technology, bringing cost of transistors down, bringing size of devices smaller, make more computational power available in smaller type of packaging, has led to a quite big revolution. A revolution where we see suddenly an explosion happening of input devices, output devices, storage devices, and compute devices. It's really where we used to have one computer per person. Suddenly you think about it, you probably own a couple of 100 processors yourself. So it's an explosion of those type of things. And you all are aware of those things: cell phones, cameras, iPods, MP3 players, displays, wireless speakers, and so on and so forth. Now, in a traditional paradigm, each of those elements was a system on its own. We take a camera, takes pictures, you take it out, at some point in time you print it out and you're done. However, my claim is that we see a change in paradigm here. Where typically, initially, function was all concentrated in a single device, what we see happening is that the functionality of those devices now becomes more intrinsic. Actually, the value is not anymore in the device in itself, but starts to become more and more the connection of the devices, the connection of gadgets. For instance, having a cell phone that connects to a computer, or a camera that wirelessly might connect to a printer, and so on and so forth, creating a ad hoc system or on-the-fly type system. So it's a fairly important change in paradigm, and it's something that people have observed already quite a long time, that this is a trend that is happening. People like Mark Weiser and things like that already in the 80s started seeing this is happening. But I think the whole idea here is best expressed by what we call Bell's law, which looks at, so you look at the one particular paradigm or measure is to look at the number of computers per person. And to make it more staggering, we're going to put it on an exponential scale or we put it on a log scale. So if you think about 1950 or something like that, there was a single computer serving the whole Earth. There was basically a UNIVAC or something that was a single device out there for everyone on Earth. And then came mainframes, became mini computers, we had desktop computers, we had laptop computers, we have palm computers, and so on and so forth. And what you see is that size was shrinking, and as a result of that, also you see that the number of people on a single device was decreasing. Actually, it's gone the other way now. Rather than having everybody on a single computer, now every single person, at least today in the developed world, is owning hundreds of processors. Think about your standard car, state-of-the-art car, one of those German or Japanese cars, probably about 100 to 200 microcontrollers in those things today. So you drive your car, you already have your 200 processors right there. So it's a paradigm that's changing quite substantially. And again, it is, oops. Again, it shows that there's somewhere a basic shift going on. If you look at the original computers, all the meaning of computation was concentrated in a single device. So your computer had all your computational functionality. What happened in the early 1990s, late 80s, with the advent of first the DARPANET and the internet and the World Wide Web, is we had the first change in paradigm, where suddenly now the single device was not the single element anymore, but basically connecting the number of devices together, we start creating computational functions which are distributed in such a way that the meaning of the computation is now in the connection of those devices. So if you browse the internet today, you have no clue anymore where the computation is being done or where the storage is being done. You disconnected those things from each other. You have I/O devices, you have storage devices, you have your compute devices. Now we go one step further. When you start basically thinking about smaller and smaller devices, we go to another paradigm, which really says that the meaning is not anymore in the connection of devices, but really in the collection. I have a collection of devices that can provide me input, output, storage, or compute, and by combining a number of them together in a somewhat ad hoc fashion, we create a function. It is not essential anymore that any one of those components is actually active. Devices might die, they might come into the game. It's a very versatile type of world. But basically, it's the collection of devices, the ensemble of devices that creates a certain function. And I think that's an important trend, and I hope we'll basically show you that some of those type of ideas might change the way we think about, for instance, running a home or basically a office or anything like that. Now, another claim I'm going to make is that most of these devices we see there, as I said, it's important that you have compute functionality. That's basically what Moore's law and semiconductor gives you. But just the compute function itself is not sufficient. You have lots of devices that have to be able to talk to each other. My claim is that most of all these devices you see there, iPods, cameras, and things like that, will have wireless interface in the future to come. Virtually every one of the devices will have some type of wireless interface. And why wireless? Well, it's got a lot of good reasons for that. First of all, cost of wiring. If you think about it, putting a wire in a home, a foot of wire is about $30. It's a shocking number, but that's really what it is. It's basically putting it down, maintenance, and so on and so forth. Other applications, it's even higher than that. The other advantage of wireless is that it's more flexible. Basically, it allows you for easier deployment and expansion of your system. Your system becomes dynamic rather than being static. It enables mobility, the fact that I can carry functionality with me while I walk around to the space that I occupy. And finally, importantly also, it enables collaborative paradigms, and we'll come back to that in a second. Now, if you think about it, as I said, come back to my number of 800 million cell phones per year. If you now start putting a wireless interface in any one of those little gadgets, your speakers, your I/O device, your storage device, and so on and so forth, we're talking about a market which, as I believe, is about a factor of at least 10 times larger than the cellular market, or order of magnitude than the number of cell phones. And this is why I believe this is a very interesting type of area to look at. It's really potentially a huge market overall. So if we do developments in the wireless space, most of the developments so far have been driven by the cell phone world. Big infrastructure, base stations, towers, and so on and so forth, I think we should actually start thinking about that application of the future where you're going to have billions of devices trying to talk to each other. And to me, the wireless infrastructure development should be driven by what this type of things need, more even than what we need to basically do data communication or voice communication. Now, obviously, I'm not the only one to be aware of that. You can see that the consumer industry is very aware of it. And here's just a set of devices that have been emerging over the last couple of years, actually over the last year or so. Basically, we talk about wireless TV based on 802.11, like Sony has set out to that. Wireless speakers, wireless tuners, cameras with 802.11 or Bluetooth type of connectivity, and cell phones that have a variety of wireless connectivity, 802.11, Bluetooth, and so on and so forth. So it is really starting to penetrate into the consumer market. If you talk to companies like Sony, for instance, they are very aware of that. And things like their ideas of basically having things like PlayStation 3 play a big role as somewhere an infrastructure component in this world is getting a lot of ground. So having all said that, I think what we might see as a result of this, assuming now that you have all those devices, you have lots and lots of devices all over the space. They're wirelessly connected. They create ad hoc type of environments. We might see some new computational paradigms that basically emerge. And one of them was dubbed, or at least Philips Semiconductor, dubbed them as one name for it. People sometimes call it ubiquitous computing. They'll give it other names. But Philips basically called it ambient intelligence. The whole idea that we have now the capability of having computational functions that are so small, that are connected, that we can basically start to distribute them in the environment, build them into the walls, build them into our daily living environment, into the furniture, into your clothing, whatever we're basically talking about. So embedded technology in the environment, hidden in the background. So it's not in the phrase in-your-face electronics anymore, but electronics that starts to disappear. As a result of that, we're basically looking at a paradigm that is reactive rather than proactive. A current compute environment is you go behind the terminal and you make it do something. You give it a command. In an environment like this, where you have an ensemble of variety of devices, sensors, as well as multimedia devices, we create an environment that can become sensitive, adaptive, and responsive to the presence of people and objects. And as a result of that, by being sensitive, it might augment our activities through smart, non-explicit assistance. Okay? So that's all the whole idea that was phrased by Philips, and it was a talk, the first time they kind of phrased this thing was around the early 2000s. And I think it's still very acutely top of, to the point today. Now, in order to make these things happen and to make it acceptable, there's a bunch of things that have to happen. Obviously, it has to preserve security. Very big thing. If you don't have security, it won't be accepted. Privacy, really important. And trustworthiness. It has to be ultimately reliable. People just, if you know the consumer world, if something is not reliable, people use it one time and they throw it away. They don't touch it anymore. So it has to be reliable. And definitely, if you start running your home based on those technologies, it has to have even larger levels of reliability connected to that. So it should use information when needed and appropriate. So that's kind of the definition of ambient intelligence. And obviously, ambient intelligence as a concept can be used in a variety of spaces. It could be used in the office environment. It could be used in the car, where, and actually is happening, a lot of the car companies are thinking about their virtual space within the car. But I believe that home probably is the premier space to start experimenting with those things. And it's going to go gradually. It's not going to be something that basically jumps in one shot, but it's basically piece by piece technologies coming together. So if you have this kind of ambient intelligent home, you can see there's a bunch of things that we basically can start imagining. You can imagine basically a home where you walk in and where the environment basically adapts to the capabilities at hand. So if I walk in and I add a new piece of hardware, be it a camera, be it my cell phone, whatever it is, it should augment automatically the capabilities that I have. So it's an adaptive type of system that adjusts to the capabilities. Very important is that it should be aware of space and topology. The quality of the service that I can get is really depending upon the place I am. and that should follow me. If I move from my living room to my kitchen, I will have a different set of capabilities, and my system should adapt to that. So it should be spatially aware. And the third one is very important. It's an absolutely essential one. It should be intuitive and self-configuring. I think a lot of us have dabbled in smart home technologies like X10 and all this type of thing, trying to automate stuff and so on and so forth. And anyone who's done it knows that, A, you have to have a licensed integrator to bring it all together, otherwise it wouldn't work. And number two, it is basically non-self-intuitive. Most people don't know, but this type of system have a very hard time turning on their TV because of the fact it's a very complex technology. And this is one of the big challenges. We'll come back to that later on. Now, you can see this in the multimedia space, and I just show you some examples here, like, for instance, on-the-wall projection, automatic type of connectivity, teleconferencing, and so on and so forth. Smart walls, all those kind of things are basically enabled by this type of capabilities. But I think we can go further than that. Because once we start playing with the home, we shouldn't only look at multimedia, voice, audio, and graphics, and so on and so forth, but there's other things that basically come into the game. The home contains a wider variety of functionalities that could be addressed by this ubiquitous type of wireless devices. Number one, very important, and something that's going to get even more important year by year, is energy management in the home. This is something that is starting to happen, and you will see it boom in the next couple of years, mostly because of regulation type of, and I'll come back to that in a second. Environmental control is also very important. Heating, cooling, and so on and so forth. Clever heating and cooling based on spatial and occupation is another type of application within the home space. Security, a lot of us have security system at home. They're totally independent of our other systems we have in our home. Basically, there's an independent network that have a bunch of detector switches, display functionality, and some actuation functionality, like turning on the alarm when somebody tries to get in. Healthcare, another one that basically is getting a lot of attention. If you go around the valley these days, a whole bunch of startup companies starting to look at, hey, what can we do with smart sensors connected to basically a cell phone network to basically help monitoring and so on and so forth. Just the first step in the healthcare space, becoming more and more important with an aging population. But this is just a subset of it. If you keep on thinking about it, once I have those set of devices out there, I can do a lot of other things, like advanced user interface. How do you interact with the home? For instance, how do you turn on a light? What we're doing today is very archaic. We have this power cable that runs to a switch, and we basically run that power cable back to that light. So we have basically power distribution and control all mixed together. Not a very clever idea. It's simple, but it's not very effective. And the last one, as already mentioned, the sense of presence in space, that you basically have a system that adapts to where you are and what you want to do. So let me give you a simple example of what can happen in this space. As I already mentioned, energy management is an important one. If any of you, I would ask you the same question. It says, you go to your home, or you look at your energy bill. You pay, what is it, a couple of $100 per month or something like that. And I ask you, do you know what component of your home uses the largest amount of electricity? Most of you wouldn't know. Sorry? Refrigerator is a big element. But actually, just to answer that particular point, it is actually pretty high. Actually, it turns out with the advent of HDTV tuner boxes and receivers, that actually standby power, just devices plugged in the wall doing nothing, are approximately equal to refrigerators. So just doing nothing already costs you quite a bit of power. It's all those adapters and things like that that basically listen and try to wait for you to do something. Very expensive type of thing. But anyhow, so you're not aware of the power. So if you would have the capability of being aware where energy is being used, that's one interesting thing. There's another interesting factor is that the cost of energy is a variable function of time. Not for a user today, because you pay a fixed price. But from a utility perspective, if somebody uses power at noontime versus at 4 p.m. in the afternoon, makes a huge differentiation. Peak power is a lot more expensive because you have to bring extra capacity online. And we're talking about factors of 2 orders of magnitude. Let's say a hot summer day in California, 4 o'clock in the afternoon, everybody gets home, turn on the air conditioning. This is where you really see very expensive spikes in power usage. Now, if I could charge your electricity at the time of usage, if you basically make that possible, and it's actually not that hard to do, you might see an automatic shift away from those peak times. And by just doing that, we can, the numbers for California are approximately about tens of billions of dollars that you can save by just making people aware of the fact that, hey, if you use power at another time of the day, in the evening, in the middle of the day, you're actually going to save a lot of, you're actually going to reduce your energy bill. So what does it take to make it happen? Well, there's a couple of factors. You need to have energy meters everywhere around. Something that measures how much power I get, something that basically tells me what the cost of power is at a point in time, also something that tells me how much different appliances use. It's a set of sensors. So we start with energy sensors. We can augment that with what we call smart thermostats. Smart thermostats are thermostats that basically take that information and based on your settings adjust how it's going to run its cooling cycle. And then you can start imagining adding other things like more temperature sensors. Today we have one in your home. If you have one thermostat, it's sitting probably somewhere next to your door when you come in, which is the worst place to put your temperature sensor. And it basically makes all the judgments on how to run your energy, your environment system based on that type of things. So it's a very distributed, very non-distributed type of environment. Just adding a couple of temperature sensors in different rooms can improve your system dramatically, helps again to give a better living environment. So the California Energy Commission has a big program on something which is called demand response. And it's trying to deploy this in the years to come, actually. There's some regulations that are coming down the pipeline today that basically will make this obligatory. It's going to be a first type of entry point for some of those wireless technologies. Lots of little sensors around in the home, basically helping you to basically cut your energy bill. It's in fact, a no-brainer. It doesn't cost you anything. $50 to $100 investment basically pays you back about in a year's time. And this is an example here of some of those activities that are happening here. A lot of companies looking at it, but it shows you that this idea of wireless sensing, distributed sensing in the home, wireless connectivity, lots of devices already is emerging through a variety of angles. Actually, to kind of put it all in perspective, I think it's worthwhile to look at this slide. I actually did this analysis a little bit. So think of your typical home and what we have today in terms of networking. And actually, a standard home in California, US, or something like that, typically has about 8 or 9 different networks running, totally in isolated fashion. You have a wired voice network, typically phone cable coming in. It's a network. You have a data network probably coming in. It could be high data rate, could be DSL, could be cable, or whatever it is. You have wireless voice. You still have your cellular, so that's another network. Think about multimedia broadband. You might have cable, satellite on top of that. Multimedia, wired. So if I basically look at my multimedia system somewhere, I have speakers, I have a number of devices, I have an AV player. What I do is I connect those things together in a star connection by wires. Security. In the security space, we have wired and wireless type of implementations. Climate control, thermostat, basically big wire going to your heating element or your cooling element through a thermostat. And then there's the home automation things like extend and so on and so forth that basically add some other functionality. So you see we have a wide range of networks that currently are present in the home, but they're all totally isolated from each other. None of them talks to each other or basically interacts with each other. Now, can you imagine that if it would be possible to link those networks together? That I can, for instance, have my security system interact with my multimedia system. If somebody rings the door, that I see a picture of the person ringing the door on your TV set while you're watching a movie. And a whole variety of other opportunities that are possible. It's just basically creating a bridging functionality between all those particular networks. So that kind of hopefully sets a little bit of tone of what I'm going after. There's going to be lots of devices that are emerging with a variety of different functions. And by bringing them all together, we create a different paradigm, an environment where hopefully our home is going to be a lot more efficient and a lot more pleasant to use. Now, in order to make this thing happen, we have the two components in it. We have on one side the high data rate type of things, which I typically will call multimedia networks. And the other side is what I would call the ambient, the things that measure space, topology, presence, variations in conditions, and so on and so forth, are basically sensor and actuator networks. Today, those things are considered as totally different animals. There's a lot of work going on in sensor networks. There's a lot of work going on in multimedia networking. However, in my perspective, those things are totally synergistic to each other. And by bringing them together, we can create a type of an experience which is a lot richer. Where on one side, multimedia networks provide the contents of what we're dealing with, while the sensor networks provide the ambient, basically the sense of presence and space that I was talking about. So let me give you some definitions before we go into some of the challenges and some of the technologies that I would like to discuss. So let me first define what a multimedia network is. To me, a multimedia network at a higher level of abstraction. It's always good to think about things a little bit higher up. What it is a set of sources, media sources, which could be a variety of things. It could be cameras, it could be DVD players, could be your cell phone, could be the internet. Set of sources of media contents. On the other side, we have a set of output devices. Wide variety of, again, displays, speakers, or storage devices like disks. I might want to capture certain experiences and put them on a storage device. And then we have things in the middle, which for the time being, I'm going to call it the router, something that connects those input devices to those output devices. Set-top boxes, media stations, and things like that. Take a set of those input devices, process the information, and send them to a variety of output devices. So a multimedia network, to me, is a collection of collaborative or cooperating algorithms designed to provide a human observer the best possible media experience, bringing contents from distributed media sources and sinks. Key factor, distributed. This is the big factor, is that now those things are not going to be centralized anymore in one place in your home, but it might be distributed through the whole space. So why is this now suddenly happening? And I already mentioned a couple of reasons for that, but it's mostly that technology has marched forward and has given us a lot more capabilities. Number one is that cameras, CCDs and things like that have become so cheap, so small, that it's almost trivial for us to provide media contents. So there's ubiquitous media I/O is basically available to you, not only in terms of sensing devices, but also in output devices. Displays are everywhere. Small displays, larger displays, and so on and so forth. Number two is that we have plenty of cheap storage. A very important element as well in the multimedia world is that you want to be able to capture it, you want to be able to store it. Storage cost has gone down substantially, and it's getting cheaper and cheaper every day. Third factor is that in the middle part, signal processing functions which you used to think about 6, 7 years ago as being outrageously expensive, nowadays go into a small processor with a limited amount of power dissipation. So we really can do very aggressive signal processing. That's the third factor. And the fourth one is this wireless galore perspective. The idea that with wireless, that it's easy to connect devices together. And I'll come back to that in a second. So let's now talk about the other side. And it's very similar. Look at this ambient world, this sensor and actuator network space. If you look at the overall abstraction here, we see something which is quite similar to a multimedia network. On one side, you have a set of sources, which could be sensors. It could be temperature sensor, a location sensor, humidity sensors, light sensors, motion sensors, infrared, whatever you think about. Cameras in itself are in a form of sensor as well. And on the other side, I have a set of actuators. Things that allow me to control heating, output displays, all those things are basically actuator devices. And in between, once again, we have a set of algorithms. In this world, we don't call them routers or anything like that. We call them typically controllers. Things that take a set of sensing, sense a number of parameters, look at them, and based on the ensemble of information they get, they make a decision to turn something on, turn it off, or whatever it is, basically control a parameter. So sensor network is, to me, a collection, again, of collaborative algorithms, cooperative algorithms, designed to achieve a set of common goals, like, for instance, heating or cooling your house, aided by interactions with the environment through distributed measurements and actions. Again, distributed is essential. They're basically spread throughout the space. Sensor networks, by its emergence, actually have created a new set of applications, which is quite staggering. That's why so many people got excited about them in the last 10 years. And it ranges from a wide variety of things like agriculture, environmental monitoring, infrastructure monitoring, and so on and so forth, which is kind of interesting. But to me, the most interesting application is where you close the loop. where you have sensing, control, and actuation. You have a feedback system. And those things are basically starting to happen in the industrial space, in the automotive space, but as I said already, also in home space is a great type of application area for this type of sensing networks. Again, the reason this thing has become compelling today is because of the fact that we have a set of synergistic technology developments. Things that are basically happening at the same time, coming together and suddenly making something possible that we already were dreaming about, but suddenly make it possible today. And first one is Moore's Law. And Moore's Law looked from a different perspective. Basically says, you know, if you scale technology, things get smaller. And chips get smaller for the same function. Every time we scale technology, the devices get smaller, easier to embed in the environment, make it disappear into our environment. The chip you see here on this finger that's an RF tag from Hitachi. It's called the Mu chip. Probably one of the smallest chips out there, 400 micron on the side. So that's one aspect of Moore's Law. Another aspect of Moore's Law is cost. Anytime we scale down, the cost per transistor goes down. 2002, I believe the cost of a transistor was about a tenth of a microbuck. Today, it's probably about another factor 10 lower, so it's about 100th of a microbuck, 10 to the minus $8 per transistor. So the costs have down substantially, so it's possible for me to start affording to have distributed computation everywhere. Number 3 is that when you want to do sensor networks or you want to do sensors, it's not sufficient to do computation, but you have to have all interfaces in there as well. Sensing functionality, power, energy, as well as our RF or interconnection interface to the world. And to make this thing happen, we have to have true system integration. We have to be able to bring these components together in a very small form factor. A lot of progress has been made in advanced packaging over the last couple of years, making this possible. And then finally, again, wireless galore. The fact that I can have very cheap, very small wireless sensor interfaces that allows us to take these things to talk to each other for very little power, for very little cost. Again, a number of synergistic factors making this all possible. So, as I said, that's kind of the introduction of the whole story. Now let's look at some of the challenges. And the biggest challenge I've faced here. So we have this huge number of devices that potentially could collaborate with each other to create some very exciting applications within the home. However, the overall challenge that we have to address is the capability of bringing novel wireless devices into such a system in such a way that it's done seamlessly and easily with little or no configuration or management, while guaranteeing the quality of the experience. So that's a big challenge. We have to have an adaptive environment, dynamic environment where we bring new elements in, and the system should basically absorb those capabilities in an ad hoc, configurable fashion, while guaranteeing, again, that the thing is going to be operational, that it doesn't crash violently on us. So what are the challenges to make this thing happen? I think there's a number of them. Number 1, reliability and quality of service. Obviously, you want to bring those things together, you expect some quality of service. How can we guarantee that in such an environment? Number 2, compatibility and portability. Absolutely essential. We have such a wide range of devices. We have such a wide range of standards and physical interfaces, nothing talks to anything. So how can we bring those components together in a seamless fashion? Very big challenge. And it's not only for today, but you have to look forward to the future. Devices that you might not even imagine yet should be able to basically incorporate it in an environment like this. Finally, or the third one, was already mentioned a couple of times, such a system should be easy to manage, easy to configure, and easy to control. And then finally, one of the biggest challenges, and I must say this is the one where I think where we see the most pitfalls sitting today, is security and privacy. As you know, things like DRMF, digital rights management, and things like that, makes this whole idea of having lots of devices talking to each other seamlessly almost impossible. So some of the impediments are in, there's some hurdles that have to be overcome to make this thing happen. So what we're going to do now is, in sequence, talk about reliability, compatibility, configuration management, and control. Given the scope of the time of today, I'm basically going to stay away from security and privacy, even though I believe it's a very important element. But some of the things I'm going to point out might help us to address some of those challenges we discussed right here. So this is the rest of the outline of the rest of the talk, reliability. And from reliability and quality of service perspective, I'm going to give you, first of all, some insight in technology developments. We're going to look at what's happening in the world of high data rate wireless for the home. What are the things that are basically on the market today? What do we see emerge? Where will things go 5 to 10 years in the future? Same thing for the low data rate wireless. The ambient side, the wireless sensor network space. Again, we're going to look at trends and developments in low data rate wireless. Then we're going to basically talk about portability, and finally about configuration management and control. So let's first think about reliability and quality of service in wireless multimedia type of systems. The challenges here that you might think about the home, and what I want to do, let's say, at the same time, I have a bunch of kids in the home or whatever it is, there's a bunch of people doing games, all this type of thing. Probably I have to shift or ship around about 10 HGTV, or 5 to 10 HGTV streams simultaneously. It's kind of a number I basically want to put as kind of the benchmark. Simultaneously, I have to process 5 to 10 HGTV streams in a wireless fashion. With a certain set of quality of service requirements in terms of throughput. Obviously, you want to make sure that your data gets through in time. And latency for some applications. Like if I want to do video conferencing, latency going to the system is very important. However, if I just watch a movie, the latency to the network doesn't matter that much. Now, there's a couple of ways of dealing with this. If I want to think about latency, throughput, and so on and so forth, quality of service, one school of thought is, gee, I'm going to make very complicated protocols that guarantee me, that set aside certain things to guarantee, let's say, a certain video throughput, audio throughput, and so on and so forth. We make very complex protocols that basically deal with real-time requirements, for instance. Now, if you look back in time, and you look at the internet, you see that people have been trying to do this for a long time, coming up with a whole set of versions of IP and so on and so forth that basically helps them to provide real-time type of functionality. Never really worked, never really was adopted. However, today you see people everywhere in the world Skyping, sending data back over, they start watching movies and so on and so forth. So what has happened there is that the challenge of basic quality of service in this case was not addressed by making very complex systems, but actually by just providing redundant, ample bandwidth. If I basically create a core of the network that allows me to ship huge amount of data back and forth in a very short time, you basically get around a lot of those problems and you don't have to worry about it. And from my perspective, this is exactly what we're going to do here as well. Rather than for the home trying to make very complicated protocols, wireless protocols that guarantee you certain latency on your video and so forth, my viewpoint is what we should do is give people ample, redundant wireless throughput. Basically infinite throughput. Let's put it this way. That's really what we're going to go after. If I have infinite throughput, I don't have to worry about all this type of things. Yes, there's some latency concerns, and we have to be able to deal with this. But in general, this basically helps you get around a lot of those things. The second thing that basically helps me to give reliability of service, something that has basically emerged from the sensor network space, is saying, gee, if I want to make sure that something stays running all the time, I can either use very complex single components with a lot of kind of guards around it to make sure that they're operational, or I can put lots of simple components down. And to me, the trend is going to this idea of lots of simple components. If one of the things breaks down, let's say I have 10 temperature sensors in my home. If 2 break down, I still have 8. I have sufficient information to keep the system operational. So this idea of redundancy, not only from a bandwidth, but also from a computational sensing and output type of perspective, gives me a sense of reliability. My application is going to be running and will degrade gracefully rather than break down abruptly. Now, you might say, that's a good idea, this infinite bandwidth type of thing, but the reality is if I look at my home today, things are not that good. I just don't have this infinite bandwidth available to me. This is what we have. If you think about it within the local area network space, there's a set of standards out there that give me some connectivity, wireless connectivity. I just enumerated them here: Bluetooth, 1 to 2 megabits per second. IRDA is wireless per se. It's based on infrared, 4 megabits per second. 802.11 ABG, giving up to 54 megabits per second. 802.11n, which you should be seeing on the market probably later this year, is going up to 108 megabits per second. And ultra-wideband devices, wireless USB basically, are starting to emerge and probably is going to be, you will probably see the first devices on the market this year as well, in a larger type volume. 100 to 500 megabits per second, point to point, and we'll come back to that in a second with some constraints. So what we see is that I can get about 100 easily. Well, not easily, but I should be able to get about 100 megabits per second in a certain local space. However, think about my 10 HDTV streams, that's clearly not sufficient. This is not going to cut it. If I really want to basically have all those devices connected together seamlessly, and I want to have infinite bandwidth. Even with 108 megabits per second, if I start putting really 2 video streams, HDTV streams together, I'm basically busted. You're not going to make it happen. So we have to go one step further than that. So my vision is that a gigabit per second is absolutely essential to make some of those things happen that I want to talk about. Now, my claim is that a gigabit per second is clearly within reach. And we will see over the next 1, 5, 10 years, a number of technologies roll out that will make this thing happening. That we're not going to have 1 gigabit per second. I think you might have way more than that. And what I'm going to do now for the next half hour before we have a break is to go to some of those technologies. Think about some of those emerging things that are happening and that will make that gigabit per second a reality. And they come from a variety of corners. Number one is what I would call just make better radios. That's number one. Improve spectral efficiency. That's really what has been the holy grail of the wireless industry for a long time. You have a certain amount of spectrum. You want to get a certain amount of data through it. What you do is you increase the bits per second, per hertz. Spectral efficiency, basically. And if you heard about 802.11n, and I'll talk more about that in a second, it's exactly doing that. It's trying to improve spectral efficiency by using multiple antennas. MIMO, as it's called, multiple in, multiple out type of antenna systems. So that's one approach. Another approach is what we call outlay. In order to provide more bandwidth or more spectrum, what we can do is to merge or go to areas where nobody ever has been. Basically start exploiting new spectral areas. Things like, for instance, 60 gigahertz. All the wireless functionality today that you play around with in your cellular bands, video, TV bands, ISM band, and so on and so forth, is all between 0 and 5 gigahertz, approximately. However, there's a wealth of spectrum out there at 17 gigahertz and 60 gigahertz. Huge opportunity for us to give wide data rate, high data rate type of wireless LANs. We'll talk about that in a second as well. And then the third one, which I think is the most appealing to me, is spectrum stealing, or borrowing, let's call it this way. Or another word for it is recycling. It's saying, gee, if you look at the spectrum utilization that's out there, the FCC tells me, with their big charts, that everything is very occupied. Everything is taken. And then you turn on the spectrum analyzer, and you see there's nothing. Most of those bands are not used. So why should I not be allowed to borrow this temporarily? So this is the idea of cognitive radio. It's getting a lot of traction these days. Obviously, it's going to take a long time for this to really make true because you have to get to regulation, standardization, and so on and so forth. But it's something that is getting a lot of attention. And once this is happening, I think spectrum will basically be for free. So we'll come back to that as well. So here's the landscape of the wireless in the home today. A bunch of IEEE committees that have basically issued a number of standards. You're mostly familiar with the 802.11 standards, which is ABG. And there's a whole bunch of other ones that are emerging, but these are the most important ones. 2.4 gigahertz, 5.4 gigahertz band. Then we have the area of what we call WPANs, wireless personal area networks, covered by things like Bluetooth, 802.15.1, Zigbee, we'll come back to that as well, is 802.15.4, and ultra-wideband is 18.15.3a, or 15.3. We have WMANs, wireless metropolitan type of networks. Things like WiMAX, for instance, are emerging that are not really covering the home, but will play a big role in the home as well. The idea that you basically have wireless distribution not at the cellular space, which is miles and miles and miles, but more on a denser type of space. Things like WiMAX, for instance, will play a big role. There's the 802.16 committee. And then finally, there's the 802.20 committee, which is basically the same thing as what the WMAN does, but in a mobile fashion. The original versions of WiMAX, for instance, were mostly for non-mobile type of applications. So it's a very wide range of things, and then there's other things emerging like 802.15.3c, which is your 60 gigahertz millimeter wave type of thing I already alluded to. We'll come back to that in a second as well. So there's an interesting thing that has happened, and I think a lot of the underlying ideas of all those things that are emerging is based on some change of philosophy within the FCC. The FCC, by the way, spectrum regulation, by the way, if you might be aware of this or might not be aware of it, the idea of spectrum regulation started with the Titanic event. It was the first time that, before that, everybody could do anything they wanted to. And then Titanic happened. Turned out they had a whole collapse of the wireless type of functionality. Everything was collapsing with each other, nothing was regulated, nothing could talk anymore, and so on and so forth. And at that point in time, Congress in the US basically decided to set up a regulation body, FCC. It was the direct result of the Titanic disaster. And they have basically stuck to this technology forever. I just say, what you do, you take your spectrum space, and you chop it into pieces, and people can either buy it, or they get it, or they basically license it, or whatever it is, a bunch of things to basically get spectrum. Very regulated, basically saying in this particular band, those are the persons that can have access, and that's what they can do. What we have seen as a trend, however, is that people start to realize that technology has gotten better over the years. We can make technology that understands what's going on in the wireless space. And as a result of that, the FCC gradually but surely, over the last 15 years, has started to kind of take its fingers away, has basically started to loosening regulation in a number of ways. And it started with the ISM bands, which were initiated in the 1980s. The ISM band around 2.4 gigahertz and the one around 900 megahertz. And then it moved to the unibands. Uniband is the 5.4 gigahertz band. And you already see that from going from ISM to uni, we see that the number of regulations, number of requirements that allow you to transmit in that particular area have been loosening up. And then we have things like millimeter wave, 60 gigahertz was opened up in 1998. We see again, it's the only control here is on total transmit power and spectral density. There's no rules anymore on what modulation scheme to use, what link control, what out of band transmission. All those things have basically been loosening up. And then the big breakthrough was ultra-wideband. The fact that suddenly the FCC allowed people to transmit over on top of other signals was quite a breakthrough. It was actually a historic type of change in philosophy. And in 2005, another thing happened. This was the first introduction of some of the cognitive radio. We'll come back to in a second, but which has virtually no rules at all. So we see that the tendency of the FCC has to basically be loosening up, make things more flexible, make spectrum reuse a lot easier for people to play around with. And as a result of that, I think this is really what's leading to this massive amount of bandwidth that's going to come our way. So let me walk through some of those technologies and give you an idea of what's going on and what the different underlying concepts are. First of all, let's talk about the idea behind 802.11n. So all of us now have laptops which have probably B or 802.11a or G in them, 54 megabits per second. Okay? The way they got there was through very clever modulation schemes, very clever power control, and so on and so forth. Basically, improving the bits per second per hertz by doing more processing. That was the idea of basically OFDM, was the idea basically of CDMA with some of the earlier version of 811 and so on and so forth. What's happening with N is the following thing. It says, gee, the problem is if I have wireless base station and wireless terminal, actually within a typical home environment, you see there's not a single path between source and destination, but there's multiple paths that the wireless signals will take. It basically bounces off the walls, goes through walls, gets reflected, diffused, and so on and so forth. So a wireless signal comes to you from your base station via a number of paths. What 811 is trying to do is say, well, gee, if that happens, I can actually, if I can estimate from what path that what I get basically the strongest signal, and rather than basically taking a single path, I actually can adjust myself. I can take the path that gives me the best possible signal. Or I can combine a couple of those signals together. I have signal 1, 2, and 3. If I combine them together in an efficient way, I just get more energy into my receiver. I'm going to get a better signal. And the way you do this is basically by having multiple antennas. So you put multiple antennas at the sender, you put multiple antennas on the receiver, and in this way I can manipulate the way I basically transmit my beams and how I receive my signals at the receive end. And theoretically, you can show that this is a wonderful idea. It really helps you to increase what we call the bits per second per hertz. I can jam more data in a limited amount of bandwidth altogether. But you have to be aware that it doesn't come for free. Those algorithms tend to be fairly computationally hungry. It basically requires on-the-fly matrix inversion, on-the-fly QR decomposition of some of your signals, so you have to have a powerful processor that sits there. So don't expect when 811N is coming out this year that this thing is going to be more power efficient than your previous generations. Actually, it's going to consume more power because the computational complexity is definitely higher. Substantially higher, by the way. So the good news is that early 2006, there were a number of people that basically jumped on the gun. A company like, for instance, Ergo had a 811N implementation out about 3 years ago. They called it pre-N. And Belkin has been selling this thing for the last 2 years. And some of you may have played around with it. And I must say, those things are quite staggering. If you used to have your little 8A, B, or G type of base station at home, you will notice that you go to the kitchen, you don't get very good connectivity. You go to another room, you might get better connectivity. Connectivity is very dependent on where you are, how your house is structured, the topology of your walls, and so on and so forth, what's in the walls, and so on and so forth. What 811N does, it gives you not only double the bandwidth, you basically go to about 108 megabits per second, but the more important thing to me, it gives you better coverage. Since I basically start playing around with this pre-N type things, I've noticed that I put one single base station down and my whole house is covered without any single problem. Because it really picks the right beam using these multiple antennas. There's about 3 antennas out there. So as I said, the good news is that the standard has been adopted. The 8.15, the 8.11N committee has agreed on the standard, and today, basically a bunch of the companies are doing what they call compatibility tests to make sure that the devices of different companies talk to each other seamlessly. So those things will be on the market very, very, very soon, mid-2006, and I think you will see this, I say any time now, you'll be able to see these things happening. But as I mentioned, those things are going to be more power hungry. It's computational power, so for small mobiles, this is not a very good idea today yet. It might get better, again, with scaling of technology. And as I said, it's basically complexity. If I want to have, just to give you an idea, if I want to have multiple antennas coming in, you have data streams coming, here you have your array of antennas, you have an array of RF front ends that basically take those different signals, and then you basically have to combine those signals together. You have to do a set of FFTs. There's some number of signal value decompositions, where you're basically looking what the strongest signal is, and basically adapt to that, and then combine it all together into a real signal. So massive amount of computation to be performed, and that's why it's power hungry. So that's what we have today. So 811N to me is a given factor. This is something going to be there. 108 megabits per second overall. Real use maybe about 50, 60 megabits per second. Not sufficient for my 10 HGTV streams, or 5 to 10 HGTV streams at the same time. So what are the other paradigms that will basically help me go forward? And I'm just going to briefly walk to each of those. One of them we call underlay, which is ultra-wideband. You basically hide your signal underneath the other ones. You have overlay, where you overlay your service on top of other services. That's like the cognitive radio. And we have the far away idea is, hey, I'm going to go and move to new spectral areas, like the 60 gigahertz. Same ideas here, but the idea, if you look at each of those things, ultra-wideband, 60 gigahertz, cognitive radios, each of those things should bring me into the gigahertz or gigabits per second type of data rates quite substantially. Let me skip over that. So let's talk a little bit first about the first one is the underlay idea, ultra-wideband. You probably have heard a lot about this. It was a big hype in the late, well, year 2000 approximately is when the idea got launched. A lot of people got very excited about it. A lot of companies got formed, startups got formed, big companies got involved, and so on and so forth. And a fist fight broke out. It really was an ugly story. There was the 802.15.3 committee that was supposed to come up with a standard, has finally disbanded. There is no 15.3 standard that has emerged because people couldn't agree. So today, there's basically two ad hoc standards that are going to be playing. So in the ultra-wideband space, two very different things, no IEEE blessing for any one of those. So, so what happened is that around 1999, 2000, the FCC basically gave out a set of rulings. It says it is allowed for you to send out wireless signals on top of other ones or underneath of other ones if you basically obey the following spectral mask, which says that you can use the bandwidth between 3 and 10 gigahertz, 7 gigahertz of bandwidth, but at most you can transmit at about 41 dBm per megahertz type of band. So the power in every piece of spectrum, in every band, has to be extremely small. And the way you get signal out of this or through this is by spreading it over a very wide band. And the very wide band is actually 500 megahertz. So you have to occupy more than 500 megahertz to be called an ultra-wideband signal. Okay? So very little energy or very little power in each spectral band, but spread it over a wide range of frequencies. You have to be aware that when you do this, there's some enemies that are out there. There's some people who are fighting you, and you have to make sure that they don't basically destroy you. Like, for instance, you have around 5.4 gigahertz, smack in the middle of those 3 to 10 gigahertz band. We have the 811, we have the ISM band, where we have IEEE 811A. And if you have this ultra-wideband receiver just next to your 811A thing, they might be battling each other. They might not like each other. So what most of the ultra-wideband people do is say, well, let's avoid this thing. So we either go 3 to 5 gigahertz or 7 to 10 gigahertz. You avoid the bands which are used extensively. Even though you should be, by theory, you should be able to basically transmit this whole thing. The problem with this guy might saturate your receiver. There's some other problems emerging. WiMAX in Europe, for instance, has a band which sits somewhere up here. It's another big chunk of spectrum that overlays and fights with the ultra-wideband. And you have to be very careful that that doesn't basically restrict yourself or basically might not saturate your receiver either. So that's really the situation we see right now, 3 to 5. And that's where most of the ultra-wideband you're going to see today, the ones that you're going to be able to buy this year, are going to be sitting in this range. However, there's a lot of opportunity with scaling of technology to go to the 7 and 10 gigahertz with cheap CMOS type of devices. Now, so that was basically what happened. FCC came out, people got really excited about it, and then suddenly all hell broke loose. Because a number of people came up, or a number of companies came up with very different ideas on how to use that spectrum. The first school of thought, which was the original one, was to say, gee, the way you create a very wideband signal is to transmit pulses. A narrow pulse, if you look at it in the time domain, very narrow, becomes very broad in the frequency space. So you transmit pulses rather than taking a sinusoidal waveform and modulating it. That's what we typically do in the wireless space. So pulse-based transmission. Impulse radio, as we call it, IRUWB. Very beautiful, very nice idea. Has pretty much gone by the wayside in the 811, or basically in the high data rate ultra-wideband space. Because people came up with a bunch of other ideas to get around. Well, there was a couple of reasons that this has happened. I still think, personally, I still believe that this has some very interesting opportunities. But the main reasons for going to some of the other technologies were really to do with avoidance of some of those other type of interferers that you might have, like 811A, how basically can you notch it out. Number two is how to fit that FCC spectrum mask. Remember the one there where you have this little hub? And basically making a fitting to that spectrum mask with pulses is not trivial. And thirdly, people were used to a certain set of technologies. People knew how to do OFDM. People know how to do CDMA because they built radios like that for a long time. Pulse-based radios were an unknown. They're a different animal. So basically expecting and predicting the performance of those things was somewhat harder. And what happened basically is that conservatism won. And the leading ultra-wideband contender today is called multiband OFDM ultra-wideband. Key proponent for that is a company like Intel, for instance. So we know how to do OFDM, so what we're just going to do is do OFDM over a very wide spectrum and go that way. And this is the MBOA Alliance, which has now basically is announcing products like wireless USB. The idea of having USB devices that connect wirelessly to your computer using ultra-wideband type of transmission. Its main competition was from a variety of startups, like Extreme, as well as big companies like Freescale, that basically were stuck to this kind of based on pulse-based, but basically use CDMA-like techniques. Direct sequencing. You take your signal and you spread it out by basically using traditional spreading techniques, just as you do in let's say, your 3G cell phones. Same idea, basically. You take your signal, make it narrowband, and you spread it out by basically multiplying it with a chipping type of sequence, a pseudo-random sequence. So let me just show you a little bit what the challenges were for the ultra-wideband, the pulse-based ultra-wideband. So for instance, if you look at a carrier-less ultra-wideband signal, you transmit a pulse, something like a dipole, like this type of signal here. It's a very short pulse. You make a dedicated pulse generator, creates a certain frequency spectrum, and one of the nice things about this thing is the duty cycle of this is very small. So people believed when the idea of ultra-wideband was introduced that you could actually build extremely simple transmitters and receivers. Well, actually, the transmitters are simple, the receivers are harder. That's one thing. And the second thing, they believed that it would be a very low power when they would do so, that they actually could give you high data rates for very low power. The problem with this pulse is that this is a baseband pulse. So if you look at the spectrum, it's going to be sitting between 0 to 1 gigahertz approximately. Right? That was the first idea. Basically start transmitting in very low frequency ranges. Two things happened. The FCC basically was kind of wary about this thing. The second thing, which is a problem, is you want to have an antenna that works between 0 and 1 gigahertz. It tends to be an ugly animal. It's like a horn. And I cannot imagine my little wireless device with a horn sitting on top of that. So building antennas for the devices has been very hard. While if you go to the 3 to 10 gigahertz band, your antennas get a lot smaller. And actually creating a wideband antenna is a lot easier to do. So everybody moved to the 3 to 10 gigahertz band, also driven by the FCC, obviously. And doesn't mean that you cannot do pulse-based anymore, but you have to modulate it up. What you basically do is you take an oscillator, and you superimpose a pulse on top of that. You quench it, basically. And you get waveforms of this type, where the oscillation will determine the carrier frequency, where you center your signal at 5 gigahertz, 3 gigahertz, or whatever it is, and the shape of this pulse here around it, the envelope, will determine the bandwidth. And remember, the bandwidth has to be larger than 500 megahertz. Okay? So You can do these things, but you see it's, if you use the basically carrierless, just a pulse, dipole type thing, you can see it's very hard to meet the FCC spectrum. So that basically ruled that one out. It's doable, but it's very hard to do. So a better approach is to use the carrier-based one, where you basically have your carrier, and you modulate, you determine your envelope in such a way that you nicely fit within the FCC type of spectrum type thing. And you can play some games. There's some other spectrums of different envelopes that give you different curves. And you can see, if you do it very carefully, you can see that you can actually utilize most of the spectrum quite nicely. However, generating those pulses now becomes a lot more complex. The idea of a very simple pulse generator, something that basically has, bingo, you take a signal in, send some current through your antenna, bingo, you turn it back off, basically disappears. You have to start doing some pulse shape modulation and so on and so forth. People actually have built those things. This is an example of a chip that was published at ICC in 2006 in 180 nanometer CMOS. It's a completely integrated carrierless pulse-based ultra-wideband signal. And as you can see, it starts with a pulse generator, that's the transmitter, wideband pulse amplifier, and then you have your pulse shaper. The pulse shaper is basically creating that envelope in such a way that I meet the FCC specs. Receiver, however, is another can of worms, because now I have this very small pulse, very widely brought out, sitting basically at noise level. To get that thing back out of noise requires a lot of processing. And this is one of the pitfalls of the ultra-wideband. Again, if you believe that I'm going to have a high data rate, ultra-low power type of ultra-wideband receiver, you're going to be mistaken. These things are power hungry. And you will see this when the numbers are finally going to be published, or basically going to be enabled this year. Again, here's the thing. This thing can be integrated in a fairly small chip. This is a couple of, probably about 4 to 5 square millimeters. Here's your spectrum. You can see it nicely meets the FCC specs and so on and so forth. This is basically on the dipole system. So that's the way we initially went. But as I said, people quickly moved over to the more traditional technologies. And this is what you will see on the market from companies like, for instance, Intel and their basically collaborators. It's an OFDM-based system, just like we do for 802.11g, just like we do for 802.11a, just like it's going to be used for the 4th generation of wide area wireless networks. OFDM has become the technology of choice. What it basically is that you have a number of frequency carriers, and they're shaped very carefully in such a way that I can pack those different frequency tones very closely together. And the way you transmit information is not by using a single tone, but you code your information in parallel over those different tones by using some code words, orthogonal code words. So this allows me to have, let's say, in this case, at the 500 megahertz band, let's say you take between 3 and 5. Here's your 3 to 5 gigahertz band. There's a bunch of subchannels. I take, let's say, 128 point IFFT. Within that 500 megahertz band, I can basically set 100 different data tones and 10 pilots. So I can transmit 100 bits at the same time. And by using some coding, I make my signals orthogonal. I can send multiple systems signals at the same time. And this is the way it looks at the frequency space. You basically have a number of frequency bundles. And the bottom line is really you have to do very, very, very fast FFTs and inverse FFTs on the fly. So a lot of computation to be done, but it allows you to manage that spectrum very carefully, and it also allows you to deal with some of those pitfalls, like maybe interfering signals coming like GPS or other ones that you definitely want to be in. You actually can basically null out some of those bands. So it's fairly easy for you to shape your spectrum to fit basically FCC requirements. So the way it works is you start with your transmit signal. You do some complex modulation on it, QAM or something like that. You go from serial to parallel. So you take a bunch of bits and take a parallel data word, and then you do the DFTs or the IDFTs, put some guard intervals between the signals transmitted out, and the receiver is basically the inverse chain. As I said, fairly decent amount of processing to be done. This is the way wireless USB is going to work. It's based on this particular standard, and this is what the products that will be released either this year or next year that I already mentioned before. And just to get you some numbers, there's a bunch of those transceivers that have been realized, published, and so on and so forth. So from an implementation perspective, things are pretty much there. But just think about, for instance, here, look at the numbers here. This is for the receiver. It's about 200 to 400 milliamps at 3 volt. For the transmitter, for this one published here, 70 milliamps at 3 volt. So we're talking about half a watt power approximately, 300 to half a watt of power dissipation. Not something you're going to put in your mouse device. Okay? So it's something that is really meant for point-to-point links, high data rate, things like video transmission or so on and so forth. For instance, a good application would be transmitting from a computer to a display. It's a good application for this type of technologies. So in terms of multiband, ultra-wideband, I think they're fully integrated systems. People originally started doing so germanium. CMOS is coming. There's some challenges still to be overcome. Coexistence with WiMAX is a big issue. People are very worried about that. But it's on a roll, will happen. And wireless USB is one of the key examples of what's going to be used here. So let's look at some other areas. So ultra-wideband is overlay or underlay. You basically hide your signal underneath the existing systems that are out there. 60 gigahertz, the idea there is to say, well, gee, why not go to somewhere where nobody is? And the good news is that around 60 gigahertz, there's about 7 gigahertz of unlicensed spectrum available, free. And the reason that it's for free is because it's really bad spectrum. They gave it away for a good reason. It's called the oxygen absorption band. This is where your electromagnetic waves start to interact with the oxygen molecules in the air, which provide a damping factor, loss factor. So you're not going to use this to transmit tens of miles, unless you have very directional antennas. But the loss factor doesn't play at all, or doesn't matter at all if you basically work on a room size. Within a room, no problem. You can easily get your signal across. So that problem is out of the way. So why have people, if the band was opened up in the 90s, why have people been very reluctant to move in there? Well, it's 60 gigahertz. That's quite fast. And before, let's say 5 years ago, 7 years ago, you had to have very exotic technologies like silicon germanium or indium phosphide to basically deal with those very high data rate signals. The good news, however, is that, again, with scaling of technology, we have now CMOS transistors that have FTs above 200 gigahertz. Actually, we can build a whole radio like this in the silicon technology, CMOS, standard bulk CMOS technology. You don't need silicon germanium. You don't need bipolar devices. You don't need gallium arsenide. So that's a big step forward. So lots of bandwidth. And the other nice news about lots of bandwidth, that's available all over the world. You go to Japan, you go to Europe, you go to the US. Every one of those countries or of those areas has basically that spectrum available. So no regulation problems here. So the challenge is really, however, designing at 60 gigahertz. It's really pushing the boundaries. Used to be that 5 gigahertz radios were hard. And now suddenly we're talking about 60 gigahertz CMOS radios. And 60 gigahertz, when you get to 60 megahertz, you start thinking about, gee, we're not talking about cluster devices anymore, but you start thinking basically about devices that look like maybe distributed devices. Your transistor might be a distributed element. Definitely your wires become transmission lines. There's no doubt about that. So you're basically in millimeter range, you start thinking about designing with transmission lines and maybe distributed type of devices, not lump devices. So people were very scared. They said, gee, when you start doing these things, there's a whole different ROM, you have to have a whole different type of designs capabilities. The answer, however, turns out when you start tackling it, and people start doing it so about 3-4 years ago, it turns out that actually those challenges are not as hard as people perceived them. First of all, at 60 gigahertz, even with 180 nanometer technology, 130 nanometer technology, if you look at the maximum stable gain at 60 gigahertz is about 7 dB. It means that with a 130 nanometer transistor, I can get gain. That was the first good news. It means that, hey, we can build amplifiers, we can start rolling. Step one. Number two is that the devices themselves could be perfectly modeled. We didn't have to have very complex new models for our devices. Actually, standard BSIM4 devices or models were doing perfectly well if they were tuned correctly. Obviously, you have to do your tests, tune your models, but once you've done that, you actually could perfectly predict how those devices would behave. So on top of that, if by using transmission line interconnect, which you know how to design, actually designing of good transmission lines on a chip is not that hard once you know how to do it, we actually could combine those elements very effectively together and come up with some fairly innovative ways of, for instance, providing resonance and so on and so forth, mixers, and all this type of things. And bottom line is, it shows that we can actually build complete transceivers. Here's an example of a 60 gigahertz receiver, amplifier, mixers, buffers, and so on and so forth. All the components are there. There's nothing basically that allows us to not to build those devices. And again, there's a couple of startups that have taken this on and actually started making devices out there in different places of the world, and both in Australia, the US, as well as Taiwan and Korea. So a good opportunity. Now, some interesting challenges, though. It's not trivial to design those type of things. For instance, one of the things that basically worries a lot of people is the fact that it's still high rate. So if you want to get your data across, you're going to have some power consumption. You might need very high speed A to D converters. A to D converters at couples of gigahertz with 8 bits or something like that could consume watts. It's not something we really want to do. So A to D converter resolution is an important one. The other one is basically how to deal with linearity, power amplification efficiency, noise, phase noise, and so on and so forth. Here's an example of tricks you can do. For instance, to avoid some of those issues. Here's an example of a 60 gigahertz receiver. You have your transmitter, you have your channel with your multipath, receiver, A to D converter, and digital equalizer. Now, in order to, if you put the equalizer behind the A to D converter, you can see that without an equalizer, there's not much you can see. Your signal is basically, a multipath basically fills up your complete eye. It's very hard to get the signal out of there. So you have to do an equalizer. But in order to make the equalizer work, I need an A to D converter which has high resolution, which is a real problem. As I said, high resolution, A to D converters, high speed, is a lot of power. So how to get around that? One option is, for instance, to make a simple analog equalizer in front of your A to D converter. Very simple. So before you A to D convert, you do your equalization. You see the eye diagram becomes a lot wider. And I can get away with an A to D converter, which probably has about just a couple of bits, saving power dramatically. Now, obviously, the quality of the equalizer is important, but here we can basically exploit digital technology to tune that very carefully. You measure the performance of the device, and then you use digital technology in the back end to basically tune your equalizer very carefully. Another thing that basically works very well in this space, as I said, multipath is an important element. We have these very, very short wavelength signals. You can see that from your antenna, you get a whole bunch of those signals in with different phase differences. So fading and all these type of things might have a big impact. However, again, this is where multiple antennas come to help. If I basically can have multiple antennas on my transmitter and my receiver, I can basically take those different signals and take them apart, like we did for MIMO. And there's one beautiful thing at 60 gigahertz, a very beautiful thing, is your antenna is extremely small. At 60 gigahertz, an antenna is about 1 millimeter or less. So I actually can afford to put about 4 antennas at the back of my chip and have my multiple antenna capability. It's an absolutely essential component, and it doesn't hurt very much at these frequencies. If I do multiple antennas at 2 gigahertz, these are big animals, and I need a lot of space to put them down. At 60 gigahertz, they're very small, but it requires some interesting processing. So this thing is definitely rolling, and I believe this is going to give us a road to 1 gigabit per second wireless LANs. The 802.15.3c working group is looking at standardization, so things are happening. Once the standards are out, things typically get into a doldrum, out of the doldrum, and things will basically happen. However, yes? This typically would go for about, with normal antennas, about 5 to 7 meters within a room. It doesn't go through walls very well. So this is basically room contained. Yes? There's shadow effects, absolutely. This is again why we would like to have multiple antennas around. It's an important component of it. Shadow effects are there, absolutely. Again, be aware that this is not for the faint of heart. You're not going to use this thing in, I talk about basically transmitter receivers that are basically a couple of watts to basically operate this frequency. Yeah, very high frequency stuff typically costs you power. There's nothing you can do about it. So, but again, it would open us the capability of getting a lot of bandwidth. So finally, before we break, let me say one more word about the overlay technology, the cognitive radio. This is the newest kid on the block, and to me has the largest potential, ultimately to give my unlimited bandwidth. The FCC in 2003 recognizes the opportunity for this space and says we recognize the importance of new cognitive radio technologies which are likely to become more prevalent over the next few years and which hold tremendous promise in helping to facilitate more effective and efficient access to spectrum. This is your spectrum map. As I said, totally filled up. This is reality. You take a spectrum analyzer, you look between 0 and 6 gigahertz. Let's say look from 3 to 6, and this is what you see. There's virtually nothing happening. There's a couple of, you definitely have the cellular bands. Well, these are sitting right here. You have your ISM band around 5.4. There's some other stuff going on. Very intermittent, but not very utilized. If I basically would be allowed to use that spectrum, borrow it on a temporarily basis, boy, could I transmit quite a bit of data. So what's the idea of cognitive radio? And as the FCC is defining it today, it says, well, there's going to be what something we'd call primary users. A primary user is the one who owns the spectrum. You basically got allocated that spectrum historically, or you paid money for it, or for some other reason. So you have your primary users, and the idea of the cognitive radio is that you make a radio which is clever enough that it can sense the spectrum and detect the presence of those primary users and position itself somewhere in between where there's nothing happening. So you reliably detect the presence of the absence of the primary users and transmit in a primary user band only if detected as unused. Sounds like a great idea. It's quite challenging, though, because detecting or sensing if something there is not something which is totally trivial. You might, for instance, have hidden terminal effects and so on and so forth. You might not hear what your neighbor hears, and so on and so forth. And if somebody comes in, the idea is that if a primary user comes back, I just basically move myself across to other spaces which are available. Now, in order to build those things, we require some interesting new technologies again. It's a new challenge for computation. Because now I have to have, first of all, a set of sensors. A radio that sits there and monitors the environment, figures out what's going on, listens to primary users if they emerge. Based on that, it has to make decisions on where and how to transmit. And then finally, you have to basically transform it into the signals which are needed for that particular band. So what this alludes to is, first of all, we're going to have clever RF technology, wideband technology. We have to have very clever sensors, and we have to have flexible radios. The return of the software-defined radio, in other words. Most of the radios in the cognitive space, by nature, going to have to be flexible structures, mostly programmable back-end type of radios, even front ends. And making those things power efficient is going to be quite of a challenge. So basic idea, as I said, you have your sensing antenna. Here's your sensing radio, which basically looks at receivers. It tries to block some known. The problem now is I have a wideband receiver, and I'm listening to everything. If there's a very strong blocker next to me, like an 811, it's going to saturate my amplifier. So if I know those things are there, I'm going to block them out. So blocking suppression before I do A to D conversion, and then I do my detection, and based on my detection, I basically set up my traditional transmitter receiver. So some interesting challenges, but people are starting to overcome them in terms of how can I basically do this dynamic range thing? What do I do with blockers? Can I use filtering? Can I do adaptive cancellation? And so on and so forth, multiple antennas, all this type of tricks. I'm not going to go into a lot of details here, but just some examples of what people have come up with. Yes?
If you have two targets and their radios next to each other, do they fight?
They have to basically talk to each other. There's every one of the standards that's coming out of there basically provides what is called a control channel. Control channel where you negotiate how to use that particular piece of spectrum. Absolutely. Yes? That's right. It's a big challenge. That's why a bunch of companies, like your traditional cellular providers are very worried about this because they have their spectrum area, they optimize their receivers for utilization of that, and then say, gee, somebody's going to start spilling into my area. I really hate this. Qualcomm and other companies like that are very scared of this. Other companies like Intel on the other side basically are pushing really hard for that. But you're right, so you have to be very careful, and it's going to be very constrained type of usage patterns. If there's certain areas known to be very sensitive, you're going to have to stay away from it. So that's why I'm saying the biggest challenge to this thing is going to be regulation. How can we move forward to deploy these technologies? Technology-wise, we can do it. The question is, how can we deploy in such a way that all the constituencies are happy with it? So what has happened, and I just, for the sake of time, what has happened is that a number of things has happened. Is that IEEE, under basically the first thing that happened is that the FCC basically opened up the television bands to do some experimentation in this space. As you know, the television bands today are very underutilized. Because of separation, there are analog television channels. So because of separation between interference again, what people have done is say, well, gee, in a certain area, if you use channel 2, you cannot use channel 3. Channel 3 has to stay void. But you can use channel 4 and so on and so forth. So what the FCC has done is opened those television channels which were unused for cognitive usage. And this is the 802.18 working group is basically working on a number of schemes to basically allow for cognitive use in those bands. So very limited spectrum range, not yet in the areas that we really would like to go, but clearly basically a first experiment in opening up spectrum. And there's actually two different types of devices that have been described now, mobile and non-mobile devices. Like for a non-mobile device, it's required that it has a GPS receiver, that it can detect where it is, that it knows what television channels are out there, so they can avoid them. The mobile devices are somewhat simpler, but have to transmit at lower power levels. But bottom line is these things are happening. Cognitive, there's, in this area, 802.18, there were two competing groups. They have agreed, so actually a standard is rolling out, and we'll see cognitive use in the television bands in the very near future. So bottom line, I think I hope I showed you that there's a bunch of new wireless technologies that are emerging in the high data rate space that will allow us to get bandwidths in excess of gigabits per second. And to me, once you get there, it starts opening this door for ubiquitous, unfretted type of wireless multimedia communication, which is really essential for the rest of the story I'm going to talk about after break. So what we're going to do in the second part is three things. Let's look a little bit at the other side of the wireless space, which is the low data rate. Because as I mentioned, if you look at this ambient intelligent environment, there's clearly two different aspects. In one sense, you have the high data rate information contents distribution. On the other side, I have the need for control information, sensing and control, which typically tends to have far less requirements in terms of bandwidth, but by its nature, it tends to be also more distributed, has to be lower power, has to be basically cheaper as well as you have more components. So we're going to talk a little bit about what's happening in that space, and then I finally will address two other things that I mentioned. Number two is portability, and finally, user-friendliness or ease of deployment. So that's kind of what basically is in store for the next hour and a half. Trends and developments in low data rate wireless, portability, and configuration and management. So this is just a repetition I've already showed. If you look at the sensing part or the actuation part, the low data rate part, what we see is a variety of sensors, typically wireless, talking to a set of controllers, or algorithms, as you can call them, and controlling some actuators to perform a certain function. Now, this is really the realm of what I would call the disappearing electronics. The idea that I can start putting those sensors everywhere around, in your walls, your furniture, clothing, whatever it is, to sense what's going on, basically do space sensing, and then basically transmit that information. Now, for this to really work, we really have to think about nodes. To really be successful in this area, to really have penetration, we need to have nodes that are really tiny, very cheap, and very low power. Absolutely essential. If you don't have that, basically deployment will be impossible. Give you an example, for instance. A lot of you probably have those kind of smoke detectors at home. Somewhere those type of things you buy at Home Depot or whatever you go to, and you stick them on the ceiling with a D battery in there. Runs for about a year, and then in the middle of the night, suddenly it starts beep, 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 beep. It's always in the middle of the night. So the first thing you do is remove that battery and never turn it back on again. So imagine now that you have hundreds of those nodes around in your house. You're going to walk around and replace batteries continuously? Absolutely not. So from an energy perspective, if you start distributing sensing capabilities, my conjecture is that every node you put down should be energy self-contained for the lifetime of the product. If the product has to be there 10 years, it basically should run 10 years on a single battery charge or find a way of recharging itself. So where are we in this space? Well, as I mentioned, wireless sensor networks have gotten a lot of attention over the last, since the late 90s. And today you can go to a set of companies and buy nodes from a variety of aspects. You go to companies like Crossbow, go to Intel, Infineon, Ember. There's some other ones out there basically making small nodes that are approximately a couple of cubic centimeters in size, consume between 10 to 100 milliwatt, and going to cost you about $50 to $70 a node if you buy them. That's really where we are at today. It's a good entry point, but not sufficient. In order to really be successful, to have that energy self-contained, we have to look at nodes that are a couple of cubic millimeters in size, consumes tens of microwatts. And I'll come back to that, why I believe tens of microwatts is important, and costs $1, $5, something in that range or less. Okay, so extremely cheap, low power, small is really what we're after. So that's really what they're looking at. Energy self-contained sensor node, something of this size. This picture here, this is one same copy of the same thing. Solar cell, basically driven power, some electronics on the back, basically sensors, some transmitters, and so on and so forth. Something you can stick on the wall, basically disappears, and you can forget about it. You never have to replace the battery for this type of thing. So in order to get there, we have to do bring a variety of technologies together. You have to really think about non-orthodox approaches, because those power levels are really an order of magnitude to 2 orders of magnitude lower than what's available today from a typical industrial perspective. So think first about the power. Assuming that you have a single cell, small battery side, like a little circular cell or something like that, you should be able, if you have a 100 microwatt node approximate, it will run for a year. Now, for most of that application, the home type of space, a year is not sufficient. I have to be able to extend it to 5 to 10 years. So very often we have to supplement the energy of the battery. The battery is really a storage device. And we have to supplement it with what we call energy scavenging, getting energy from the environment. And there's a set of sources, light, vibration, other ones we'll briefly talk about. But energy scavenging is an important component here. Number two is we have to rethink the way we build radios. Most of the effort in building wireless transceivers has always gone towards higher data rates, complex modulation schemes, all those type of things. Ultra-low power has never been addressed to the core. When you think about power, and you say power is the most important thing, you're going to design a radio very differently than you would do, let's say, your 811 type radio. So non-orthodox radios with minimal number of external components are absolutely essential. Combined with that, we need very low power digital processing. Digital processing that basically have, most importantly, very low standby power. Because most of those nodes, those location nodes, sensor nodes, and so on and so forth, work on very low duty cycles. Now, if you have a temperature sensor, for instance, it's maybe it transmits a piece of data every second or a couple of seconds. Duty cycle extremely low, power is going to be dominated by standby power. So basically getting standby power to virtually zero is absolutely essential. Leakage factors and so on and so forth, monitoring, protocol level type thing, all very important. Because it's not sufficient to just go to control leakage, it's also protocol. For instance, if I have a radio that's off most of the time, it's very hard to have a meaningful communication with it. If I have one radio here, another one here, not synchronized, how do you talk to a radio that's asleep? So you have to have protocols that allow nodes to synchronize while basically mostly being asleep or in very dormant style modes. So all those technologies come together. So what's the industrial state of the art in this space? Well, For a long time, low data rate, as I mentioned, was pretty much a non-issue. Nobody was really looking at it. And the only thing that really popped up in the late 1990s that was somewhat a useful type of entry point in this space was Bluetooth. Bluetooth was came out around 1997, 1998 approximately. And the original goal of Bluetooth was basically to act as a wire replacement. And I'll talk a little bit more about Bluetooth. Something that looked for a long time like a technology that was wanting for an application had become a lot more successful. Today, actually, finally, Bluetooth has come to the point that sales are basically volume had become quite meaningful and basically starting to get to the levels that the hype basically was predicting 7 years ago. What else is there? There's 18.15.4, which is often called Zigbee. And I'll talk a little bit about the history of this, which is actually the first wireless standard that's out there that's looking at low power, low data rate wireless for low power applications. So far has been very limited in its success, hasn't really made a huge inroad whatsoever. Might change, but it has some limitations. Actually, by the nature of the standard, the way it was built, power is still a big issue, and it's, in my perspective, a factor 10 at least higher than what it should be. They're basically marginally meeting the application requirements. So a lot of people are stepping away from Zigbee to go back to what we call in-house ad hoc protocols. Some interesting things are happening in terms of developments. 8.15.4a, which is a variant of the Zigbee, or the 8.15.4 protocol, but based on ultra-wideband, is something that's is getting some traction. I'll talk about that. And as I said already, most companies, actually a lot of companies using proprietary protocols in 800 megahertz unlicensed band, because they're very, very simple protocols, very low power, very cheap. The garage door opener type of wireless type of interfaces. So let me go to one of those things and then project what is possible, like we did before. Everybody's now familiar with Bluetooth. As I said, basically was introduced as a wired replacement. It's a mostly analog radio, the way it was perceived. It was not really going after digital space. It's a fast frequency hopper. What it does is basically changes frequency very, very, very rapidly. Actually, a number of times per bit, your transmitter is basically changing frequency, and your receiver has to track that. About 1 megabits per second, operates in 2.4 gigahertz band. Typical power is about 30 milliamp of overall current at 1.8. So we're talking about a 50 milliwatt type of transceiver in the Bluetooth space. And volume definitely is there. Now, people predicted that for Bluetooth to be successful, you have to have chipsets below $5. They're there. So we basically have now Bluetooth that below $4 overall in volume. So interesting technology. However, it had a lot of pitfalls. The reason that Bluetooth was not successful, has not been successful in the sensor space, is for a couple of things. A, it was designed by a cellular company. So the whole protocol was designed with a set of things in mind, like voice. Voice is important, so voice had to be basically supported very well. There's a bunch of other factors that basically in there that makes basically making low power Bluetooth a very hard thing to do. And 50 milliwatt is fairly high for the application we're talking about. You're not going to run things for years on a 50 milliwatt radio. A couple of operational modes. If you look at the Zigbee span, you can actually transmit at different levels. There's a 0 dBm type of mode, which is 1 milliwatt transmit power, which gives you about 10 meters. But Bluetooth also allows you to transmit at higher power levels, 4 dBm and 20 dBm, which allows you to go to far larger distances, to hundreds of meters, basically. So a number of people started playing around with Bluetooth for the sensor space, but most of the people basically dropped it because of the power concerns. Then came 8.15.4. Now, it's an interesting story how it all came together. 8.15.4 has a long history. Some of you might remember that at the time that Bluetooth was launched, there was another initiative that was happening with companies like Philips, Intel, Toshiba, and so on and so forth, which is called Home RF. The idea of basically creating wireless connectivities within the home, between a set of devices, and so on and so forth. So home RF was, at some point in time, very strongly competing with Bluetooth. They were considered as competitors for each other. Now, home RF never materialized, and at some point in time, I think in 2001, the home RF working group was disbanded. People figured out what's the end. The standard was written, everything was done, but nobody ever built any parts. However, it refused to die. And there was another group that basically took, and especially within Philips, they created a program which is called Home RF Lite. It was a lightweight version. They realized there was a need for very cheap, low power, low data rate, short distance type of radios for things like toys and so on and so forth. That were kind of the application they were looking at that point in time. So what basically happened is that they took the home RF specs and kind of simplified them, narrowed them down, changed the data rates, and so on and so forth, and call them Home RF Lite or Firefly. Now, Firefly didn't go very far either. Again, was turned around, was the idea. If you look at the goals of Firefly is 150 kilobit per second data rates, 10 meter type of distances, networks with about 30 to 200 nodes, some location capabilities, 2-year battery lifetime was kind of the goal for Firefly. Kind of disappeared, and suddenly out of this thing popped up Zigbee. So Zigbee is really a kind of a redressing of basically what Firefly was all about. So we called it Zigbee, created a physical layer and a link layer. That was the first step what Zigbee did, and then turned it into a standard IEEE standard which is called 802.15.4, which is a physical layer for low data rate type of devices. Data rates of 200 kilobits per second, 40 kilobits per second, 20 kilobits per second. 2 different addressing modes, 16-bit short and 64-bit IEEE long. Support for some critical latency devices. Like for joysticks, one of those applications you want to make sure, when you have joysticks, you want to make sure that latency is taken into account. It's not known of the CSMA collision avoidance channel access. Fully handshake protocol for transfer reliability, so it's a reliable link. And there's very important that they started thinking about power management, something that was not done, for instance, in the Bluetooth space. The idea that if a device is not operational, I can shut it off. Very important entry point, because that helps a lot to basically reduce power. There's a couple of different frequency bands it's operational in, 2.4 gig, 19.50 megahertz, and the 1868 megahertz band, with different type of channel numbers available. So depending upon the region in the world where you're at, you basically have different frequency spectrums that basically are covered. Because regulations between Europe, Asia, and the US are basically different. For instance, the 915 ISM band is only in the US. So here's an example of one of the most successful 8.15.4 radios. Was built by a company called Chipcon, which is now Texas Instruments. It was a Norwegian company, and has recently, about half a year ago, been bought by Texas Instruments. So this is a 2.4 gigabits per second, 2.4 gigahertz radio. Basically gives you 250 kilobits per second direct sequence by spectrum at 2 megachips per second, 16 channels, 1.8 volt supply. Now, one thing I would like to point out on this particular slide, it's kind of small, but I think you have to look at the current consumptions here at a different rate. So we're talking about, if you look at the overall numbers, about 20 milliamp at 3 volts in terms of transceive power, which means about 60 milliwatts of power dissipation. Not basically in the same realm, actually, maybe a little bit lower. Some of the implementation are about 30 milliwatt, but typically in the same realm of Bluetooth when they're operational. But however, remember, they have a much better power control capability, power management capability, so you can actually turn off the radio or manage the on time of the radio a lot better in a Zigbee or an 8.15.4 type of environment than you can, let's say, in the Bluetooth space. Now, one thing I want to point out, however, is if you look at this particular chip, the Chipcon radio, what I plot here is the power dissipation. This is the received power dissipation. It's about 60 milliwatts. And this is the transmit power, depending upon basically the data rate. Upon basically the data rate of the, power efficiency, depending upon the distance of the transmission. And as you can see here, if you look at the transmit power, basically varies from about 3 microwatt to about 1 milliwatt. So 1 milliwatt gives you 10 meters of distance approximately, maybe 20. 3 microwatt would be for distance which are very close to each other. So most of those radios allow you to control the transmit power. However, you can see there's a huge variance in the transmit power. If you now look at the total transmitter power, the power consumed by the transmitter, you see that actually goes between 25 milliwatt to about 50 milliwatt, while ranging the transmitted power from 3 microwatt to 1 milliwatt. What this shows that this is a very inefficient transmitter. To basically get 1 milliwatt out of the antenna, I basically consume 50 milliwatt of power. If I basically use 3 microwatt of transmission, I still use 25 milliwatt of power. So the efficiency of this antenna, of this transmitter, is between about 0.1% to 2% efficiency, if you look at the transmit efficiency. And that's, to me, one of the big Achilles heels of this particular radio. The fact is that if I want to transmit, if I want to build a good transmitter, what I want to make sure is I optimize the whole thing. If I want to transmit 1 milliwatt, I don't want to basically spend 50 milliwatt to create that signal. Okay, so getting that efficiency up is absolutely important if you want to get better radios for low data rate transmissions. Just as another side note, so 8.15.4 became a standard. At that point in time, the Zigbee consortium, it's a consortium of, like always, a couple of hundred companies, but driven by a limited set of companies, repositioned itself. And today, Zigbee stands for the Zigbee Consortium, basically doesn't deal with physical layer or link layer at all. That's basically 8.15.4. And what they basically help define is a set of layers on top of the 8.15.4 protocol. It's basically networking, presentation layer, application layer, and so on top of layers. So it's a higher level perspective, which is absolutely essential if you want to deploy those networks in a scalable fashion. Another thing that's happening more recently is the 8.15.4 development. As I mentioned before, when ultra-wideband came out, people basically positioned it as a high data rate, low power technology. So we figured out how to do the high data rate. 500 megabits per second is not bad, but the low power part never happens. The idea is, how you transmit pulses, what can be easier than that? It should be a trivial transmitter, and yeah, the receiver is just going to be a little bit. Never worked. Basically, if you look at the receivers for the high data rate, they're high power. But people still saw the opportunity for using ultra-wideband for the low power range. And that's really what 8.15.4a is trying to do, is an ultra-wideband, pulse-based, going back to the roots, pulse-based type of standard for low data rate, low distance, soul distance type of applications. And the good news is, again, that it seems that the whole standardization process is converging. And there's now a draft proposal on the table. I'm not sure if it's been voted through completely, but it's basically an 8.15.4 standard available. Actually, there's 2 versions. One of them is between 3 and 5 gigahertz pulse-based. The other one is a chirp-based version. Both are basically have been approved by the committee. So this is something that's happening, and which is interesting, because if you read to the definition, you go to the 8.15.4a website, one thing they point out very clearly, and it's hard to read, but basically one thing that's absolutely essential to this particular version of the standard is the locationing aspect. Locationing is an integrated aspect, or ranging is an integral part of the standard. In the sense that if I transmit pulses and I can measure time of flight, I can measure distance between different nodes. And so this is why the 8.15.4a is basically getting a lot of traction, because locationing, as I mentioned before, position awareness is absolutely essential for some of the applications we're talking about here. And this seems to be offering it. Obviously, we have to await actual implementations. So that's an interesting development. Standards are out there. I haven't seen any chipsets yet, but I think you will see some of those things pretty soon. As I mentioned, the most important developments that I've seen in the sensor network space so far for low power are basically these proprietary implementations, where people build very simple on-off keyed, frequency shift key type of radios. They are cheap, not very sophisticated, small board, fairly simple to distribute, not very reliable, however. Here's an example of one of those radios. This is from Infineon. It's a 0.5 micron technology, nothing really fancy. Data rates of 64 gigabits per second, but power dissipations of about 10 milliamps at 3 volts, so about 20 milliamps approximately. Fairly cheap technologies and very ubiquitous. That's so that's where we are. So you have Bluetooth, 8.15.4, 18.15.4a, and some commodity ad hoc standards. So the question is how to go forward. As I mentioned, I think in order to be successful in this space, we have to bring down the size of the nodes, power dissipation of the nodes, a factor of 10 down at least. And I use the number 100 microwatt. Actually, in 1999, my students and I started a project which is called Pico Radio, which basically said, is it possible for us to build radios that go at, let's say, data rates of about 100 kilobits per second, are below $1, smaller than a cubic centimeter, and less than 100 microwatt. Now, why 100 microwatt? Well, mostly of this thing is driven by the energy concerns that I already expressed before. In order for a node to be acceptable, it has to be able to run for about 10 years in a self-contained type of mode. So the first question you have to ask when you start building a radio like this is, what can I get? How much power do I get based on a piece of volume? And I put on the number of cubic centimeters. So what can we do with a cubic centimeter? So you look at battery technologies. What can I do with a given battery? So you look at primary batteries, alkaline, gives you at about 90 microwatt per cubic centimeter per year. So if I have a radio that consumes on the average 90 microwatt, I'm going to be able to run for a single year with a cubic centimeter of battery. If you take rechargeables, you lose a factor of 3 approximately, 34 microwatt per centimeter cube per year. Hypercapacitors is another form of basically storing capacitors, basic supercapacitor and so on and so forth, have been improving quite a bit over the last couple of years, by the way, but still is about a factor of 10 worse again than what is a secondary capacitor could be. And then obviously we might have fuel cells. If they ever basically become widely distributed, fuel cells could reach to about 110 microwatt per cubic centimeter per year. So it shows that by purely relying on batteries, if I have a 100 microwatt radio, or average radio, I'm going to basically run for a year, which is not sufficient. So what else can I do? As I said, you have to look at other opportunities. Scavenging. Basically replenish the energy while the node is running and replenish your batteries over time. And then you can start looking around, what are the opportunities? There's a lot of sources of energy out there. There's some really good book chapters about this. There's some people at the Media Lab at MIT. Joe Paradiso has written a very nice book chapter. There's some other things out there that describe all virtual sources of energy and how much you can get, let's say, on the human body in a typical home environment and so on and so forth. The most obvious candidate is light. You have light, it's a good source. The problem with light, however, is dynamic range is quite dramatically different. If you basically are outside in sunlight, I can get 10 milliwatt per square centimeter. More than sufficient. I can run a road forever. However, if you're in a room like this, if you get about 1 to 5 microwatt, you're going to be a very lucky person. It drops off quite dramatically. So the dynamic range of light is very dependent upon the conditions where you are. But there's other opportunities, like vibration. If you think about a typical building, there's a lot of vibration around there. Microwave ovens, fridges, all those type of things vibrate quite effectively. And actually, harvesting vibration is quite easy. Use things like piezoelectric materials, use little benders, you actually can get quite a bit of power out of this. And for instance, we've shown that we can get about, by putting a piezo bender on top of a fridge or a microwave oven, we can get about 200 microwatt for a cubic centimeter of mass. So that's actually the same thing like air conditioning ducts, other places. Airflow can give you very nice human power, walking obviously. is a good source. People have put this kind of benders in shoes, so you can recharge yourself basically while walking around. Watches, movement, all those kind of things. Temperature differentiations, pressure variations, a whole range of things. But if you look at the list, again, what you see, the number that emerges, about 100 microwatt is a number that I might be able to get. And that's really what I use as a target for the radios we assist. 100 microwatt, 100 kilobits per second, cubic centimeter tile radios. So the question is, how do you get there? And as I mentioned before, you have to forget what you learned about radios, at least in recent textbooks. You have to go back in time. Look at simple, 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 simple. You cannot do very much for 100 microwatts, so look at the simplest possible architectures that you can build. I call it the art of creativity. Rethink the way to basically transmit and receive signals. So novel miniature wireless transceivers important. Again, low power computation, innovative energy sources, and integrated sensors. All those things together is really what brings us to this 100 microwatt node. And you have to think system level when you design those things. It doesn't help you to concentrate on the radio or on the compute. You have to look at the whole system at large. What is my powertrain? How can I get the power from this to the different components? How do I translate the power and so on? So how do I store it? All those things have to be taken into account. You have to combine this with innovative packaging, because the idea of having an integrated node, which basically is all going to be on a single chip, is probably nonsensical. Yes, I can try to bring sensors, power sources, radios, digital processing, mixed signal processing, all on the same die, but you're going to end up with a suboptimal technology. Some things are done better in different technologies. So innovative packaging are very important. And here's an example, a set of nodes that were built by Philips in Eindhoven, mostly for biomedical application. They call them SAND modules. They're kind of cylindrical type of units that snap on top of each other, gives you radios, processing power, power regulation, all this type of things, transmitters. 2.5D and 3D integration, very important. Be able to bring various of components together, resonators together with radios, in such a way that we get very small density type of components. Maybe even wireless connectivity between components, something to play around. When you stack boards on top of each other, why put wires? If I want to make it cheap, maybe just wireless connectivity between boards using inductors can be done. But ultimately, and even self-assembly of components might be a way of bringing a variety of components together in a very cheap fashion. But this is really what we're talking about. This is an example of one of my, what I call a Pico cube. This is an integrated node, has 5 boards on top of each other. Think about this as a rack, a miniature rack. Has 5 boards on top of each other. There's a microcontroller, there's a radio board in here, there's a sensor board with a variety of sensors, there's a power control, so a variety of things stacked onto each other using polymer-based interconnections. So no wires between the boards, just pressure connection, and this is a complete type of in-compute communication node. So let's, so how to get to this thing basically consumes, this for an application, we built it actually initially for tire pressure monitoring, had to be power sensors. We had about 6 microwatt of power. That's really what the number we had. So I build a node that's about 6 microwatt on the average in terms of power. And there's a number of things, but the first thing, as I already said, you have to look at the radio. The question is, can I build this thing? Can I build ultra-low power RF? Things that are basically less than 100 microwatt. And the answer is absolutely yes. We can build radios that are way below your milliwatt level. But as I said, you have to think in an unorthodox fashion. And here's some ways of doing it. First of all, think about passives. Passives are good because they don't consume current. So from a power perspective, they're beautiful elements to have. And they help us to basically select signals. Without having to do a lot of computation, I can basically discriminate between different signals. Now, obviously, in order to use those passives effectively, we have to think about new architecture to create gain. The important part of a good receiver is that I get a signal and it's very weak and I have to amplify it. Right? Otherwise, I don't have a good sensitivity. So how do I amplify if I don't have current? That's the big question. Every amplifier typically takes current. That's where, again, where those passives might help. If I can create resonance, something that oscillates, it creates basically gain on itself. So basically using passives to create gain is in a way of basically building a very power efficient receiver. So efficient oscillators are absolutely essential. And this is where technology comes in. We have to keep our eye open for new technologies that are emerging. And we were lucky at the time we started this project that Agilent, I think it was still HP at that point in time, was just playing around with a new technology which I called FBAR, Field Bulk Acoustic Resonator. And an FBAR basically is, it's a membrane of aluminum nitride, which is a piezoelectric material, with 2 layers of molybdenum on top of it above a cavity. Basically, it becomes a resonant element, an acoustic element. And the size of these things are amazingly small. We're talking about 100 micron in size overall. Very small components, but the beauty of it overall is that those things have basically become basically resonating elements at frequencies above gigahertz. Actually, they've shown to work to about 5 gigahertz with Q factors of about 1,000 to 5,000. So extremely selective components, passive selective components, which now allows me to pick out a signal out of your total frequency range coming in. I can basically easily select a single frequency out of there. I can build filters, I can build oscillators that are very precise, all by these passive components. Since then, this has gotten a lot more successful. FBARs are now basically designed into virtually every CDMA cell phone that you're going to buy. There's basically a set of FBARs in there. So they're basically in volume. They cost you a couple of cents. People have also started depositing them on top of silicon. This is a chip from ST Microelectronics of ISSC last year, where you can see an FBAR basically pushed on top of a RF radio, combining the two together. So suddenly, passives allow me to build highly selective components at RF frequencies. And this changes the world. Because why do we build radios the way we did before? You basically take a radio, the way the receiver works is you have your antenna, you amplify it a bit, and then you mix it down to some IF frequency or to baseband. Why? Because it's very hard to filter at RF. So you first mix it down, filter there, do all your operations at lower frequencies. But if you can start filtering at RF frequency, I don't need any of that stuff. I can do the thing right after the antenna. And you start thinking about new type of radio architectures. Actually, this is not the end of the story. There's a whole world now of what's called RF MEMS, radio frequency MEMS components, that promises to provide us oscillators, same like the FBARs, but now in a technology compatible to silicon, that basically can fabricate it together with your silicon, and actually gives you not a single frequency, but actually a range of frequencies determined by your masks, not by the thickness of the membrane as an FBAR. And here's an example of a device that was designed at the University of Michigan by Clark Nguyen. It's a disk, oscillating disk, as you can see it right here. And that thing, you apply the input signal, and that thing is going to start to extract and basically oscillate back and forth, just in the style that you see here. It's a piece of material, you apply your input signal, and you become resonant material. This disk expands and extracts, and basically becomes a high Q resonator. Actually, people have measured Qs of about 10,000 at frequencies, again, about 1.5 gigahertz. Still a lot of problems to be addressed, but still, it shows that there's something happening here. That basically the usage of those passive components allows us to build quite simple receivers that are very selective and low power. So here's an example of a receiver that does exactly that. This was a chip that we published at the ICCC, I think, in 2005. It's actually a super regenerative receiver. Now, super regenerative receivers are nothing new. In 1920, Armstrong basically invented everything about radios. In a couple of years, basically invented the super heterodyne, basically the heterodyne radio, all this type of thing, as well as super regenerative. So the idea of a super regenerative radio is quite simple. In order to make a receiver, at that time, basically, power amplifying components were very expensive in the 1920s. They were called vacuum tubes. And if you use one, that's already a lot of them. Two is a lot of them. They take a lot of current. So trying to avoid number of vacuum tubes was really their goal. So he says, well, if I basically can use some highly tuned components, I can make an oscillator that basically oscillates. When the signal comes in, they start oscillating, you automatically get gain. So you use an oscillator or an astable element to detect the signal. So you get automatic gain without any current. And that's exactly what this chip does. It's about 2 square millimeters. It uses F-bars, as you can see here, for send, transmit, and receive. And here's how it operates. Anytime you basically have, it's an on-off keyed radio. So if no signal comes in, the radio, you basically turn on your oscillator. Your oscillator sits there. If there's no signal coming in, it typically shouldn't start up, but some noise will come in eventually, and some fluke electron will make it start to oscillate. So it will have a random startup time. But at some point in time, it starts up, starts oscillating, and at that point in time, once it oscillates, we squelch it, we stop the oscillation. However, when you have a real signal coming in, a real signal, your oscillation will start up a lot earlier. So you get oscillation starting to right here. So the blue dot that you see on this curve here is what we call the eye of the receiver. It's an on-off receiver. If it's in this track, you have a 0. In this track, you have a 1. You squelch it, you integrate it over a number of those samples, and you basically have a simple receiver, which basically consumes about 300 microwatt when on. So this is, if you leave it on continuously, you don't basically do any duty cycle, we're talking about 300 microwatt receiver using this type of concept. This is only one example. There's a lot of other ones that you can do, but it shows that you can build receivers when on, which are basically a couple hundred microwatt. You duty cycle those things, we're talking about 10 microwatt receivers, which is quite close to my goals of what I was going after. So if you can do receivers, we also have to do the transmitters effectively. And there the big challenge, what I already mentioned, is the efficiency. Typically, when people design wireless transmitters, they mention the power amplifier, the efficiency of the power amplifier, because that's the most important element. If you transmit a couple of watts, like a cellular phone, you have to throw a lot of power out there, and the efficiency of the power amplifier is really important. However, if you transmit at less than a milliwatt, the power that goes in a power amplifier is very small compared, or it's only a fraction. You have to take into account the modulator, the sine wave generators, your oscillators, and so on and so forth. You have to look at the whole transmitter as a whole. And the power amplifier is just a small component of it. And this is kind of shown that if you start thinking about this, you actually can get the efficiency. Remember the radio I was talking before, the Zigbee radio, 3% efficiency in the transmitter? So that's typically what you see. Most of the power goes in the low power amplifier, frequency synthesizers, the modulators, all those things, mixers. You can see overall, very little power goes, 30 milliwatt power total, 1 milliwatt goes out the antenna, 3.3% efficiency. But by starting to think about the transmitter as a whole, we see we can get those numbers up dramatically. For instance, I could use as a transmitter a pure oscillator connected directly in the antenna. Forget about power amplifiers. I don't need those things anymore because I only need less than a milliwatt, maybe half a milliwatt of power to go out there. So by having the oscillator going to right in the antenna is one approach. Or another approach is basically design the antenna to be part of your amplifier, part of your transmitter. It becomes part of your resonating elements. You co-design them together. And suddenly we can see we can go up from about 3% efficiency to about 52% efficiency. Basically, you throw 1 milliwatt out, the whole transmitter consumes about 2 milliwatt. And remember, the duty cycle of the things is small. Power of those things basically becomes very, very small, and overall can be basically ignored. So this is an example of a complete active antenna transmitter where we basically co-designed to transmit the antenna with the transmitter. You can see the whole chip again is a couple of square millimeters. From a silicon perspective, a couple of cents total cost. And I might have an example of one of those guys. So by doing so, we showed that here's your industrial standards for both transmitters. This is where your chip-con radios are. This shows transmit efficiency versus data rate. You see you get about 3 to 5% efficiency. By using this approach that I'm using, we got about, that I basically described, direct modulation, injection locking, active antenna, we get to about 50% efficiency. So you really can get very highly efficient transmitters. And the same thing is true in the receiver world, where your industrial standards are sitting at about 20 milliwatts, 30 milliwatts. By using those passive-based approaches, we can have 200 kilobits, 300 kilobits per second radios that basically consume about 300, 400 microwatt. So we really can shift that around, and these ultra-low power transmitters are absolutely possible. And we can integrate them together. Here's the Pico node cube that I already showed you before. It's one example. Here's another example of a radio which shows on top. This thing is a complete node. Here's a complete node. This has your transmitter receiver. But the interesting part, if you look at this board, size of a solar module, the solar module energy basically determines the size of the node. The interesting part is that a transmitter receiver chip sits right here at the edge of the antenna. This is a printed L antenna, so we print the antenna on the board, very cheap, so you don't have to have an external component. This is the transmitter receiver, basically a couple of square millimeters under this particular blob. The rest is a set of sensors, microcontrollers. There's a TI microcontroller on here, as well as power regulation. This thing needs about 3 or 4 different power supplies, so we had to use off-the-shelf power regulators, which are not very efficient and take a lot of space. Actually, a better approach is to take those regulators, design them together with the microcontroller, and you get a lot smaller compute type of implementation. So this whole thing can easily be shrunk to about a single chip that basically would sit within the 100 microwatt range that I was describing before quite easily. Okay, so I hope I described you that there's still a lot of opportunity to go in the ultra-low power space as well. High data rate can really push things out, even in the low power, low data rate type of space. A lot of opportunity left to make very small, very simple nodes. However, let me come back a little bit to the reliability issue. For the high data rate thing, it says, well, we're going to provide ample bandwidth. That's one way for us to basically deal with reliability, quality of service. In the low data rate thing, it's a little bit trickier. There's one dirty secret to the simple radios. They turn out to be fairly bad radios, in the sense that they're basically very sensitive. Since they're narrowband radios, they're quite sensitive to things like fading and reflection effects, multi-path effects, and so on and so forth. Actually, there's a challenge here. Because ultimately, I mentioned we require those systems to run extremely reliably. We want to basically deploy the system, and our house should be running forever, not break down. Now, one thing I would like to state is that if you look at this disappearing electronics concept, this ambient electronics type of concept, I believe that unreliability of the components is an essential component of that. I assume that nodes will be crashed. I assume that nodes will be running out of energy occasionally because they didn't get any power. They might be, because of cost and power and size constraint, we might have basically cut down on some of the margins as well. So I have to assume that nodes will fail. Some of the nodes will fail. One approach to get around that is, well, gee, let's back off again, make very powerful radios and so on and so forth, but then you have the power problem, and you basically end up with something that doesn't meet your specs. So the wrong answer to this approach would be to say, well, gee, I'm going to basically put margins in there. Huge margins in terms of reliability. I think it's the wrong way to look at it. To me, the better way to look at it is to say, gee, if we start thinking about this concept of ambient intelligence, this distributed electronics, I can assume that we'll have lots of nodes in my system. So rather than basically providing reliability by making my individual components very reliable, very, very basically over-designed, I might go to say, well, gee, why not use lots of them? Provide redundancy. And by using redundancy, I can build a system that even though individual nodes can break down, can disappear, can run out of power, the whole system itself remains basically operational. Let me just show you one example of how this can be done. This is a measurement using one of those radios I just showed right here. Single link, line of sight connectivity in a meeting room. You have a transmitter, receiver, and you look at the quality of the link. Success rate of packets being transmitted. This is measured over a full day. So start early in the morning, nobody's around, channel basically direct line of sight, perfect connectivity. All your packets nicely go through. Then 11 o'clock, graduate students kind of start trickling in. We have our first meeting, you fill up the room, line of sight disappears. You can see with those narrowband radios, you create a fading path and nothing goes through. All packets basically rejected, meeting finished, your channel gets good again, but a couple of people wander through, the channel basically varies quite dramatically. So this is one of the key problems of those narrowband radios is that they're very sensitive to those line of sight effects, basically fading effects and so on and so forth. So one approach to say, well, gee, I'm going to use the wideband, but wideband costs you power. Makes your nodes more complex, makes them more expensive. So here's another alternative. What I could do instead is say, gee, instead of having 2 nodes, let's put down 3 nodes. Add one more node. So I have the choice now. If I want to transmit a packet, I come directly to the destination, or I use an intermediate node to route the packet across. And what you see here is the following thing. This is the same kind of measurement, same radios. What I did is gradually move the radios across from each other. You start at 0 centimeters, and then gradually you move them with respect to each other, and you measure the channel quality. And you look at the red curve, you see very good connectivity, very good connectivity. At 90 centimeters, bing, I get a fade. Multipath effects, I get nothing across. Then it gets better again, it gets bad, gets better, it gets bad, and so on and so forth. So with 2 nodes, very variable. I add a third node to the channel. And suddenly what I see is that my channel becomes very flat. Because now I have a choice. I send it either directly or I use the intermediate node, and your packets most of the time get across. So what I'm doing is creating an average channel by basically adding more and more nodes to the system. And if you're clever, you can do even better than that. You can get better than the average channel. So this requires support from the routing perspective. So here's an example. Suppose now I have a network where I have n nodes. And I want to transmit a packet, let's say, from this node source to this destination node. Typical algorithms say, you want to conserve power, what do? You choose the shortest path. You go from this node to this node to this node, that's going to be the lowest power type of implementation. But as I said, what might happen that over time, this node disappears, ran out of energy, basically might not be there. So what your transmitter is going to start doing is trying to retransmit till it gets across, burns a lot of power in retransmission. You lose. So a much better approach is to say, well, I'm not going to basically worry about this node. I'm going to say any node at the link level perspective, any node that goes in the right direction is a good candidate for me to transmit the packet to. So rather than basically picking the shortest path, I pick the first node in the neighborhood that goes in the right direction, and then forward this, and so on and so forth. And by doing so, suddenly I create an extremely robust routing protocol based on unreliable radios. And the overall power dissipation gets reduced, as well as the reliability gets increased. I almost can guarantee that a packet will get across in this type of environment. So using redundancy as a means of providing reliability is another way that basically is going to be quite essential as part of this paradigm. Okay, so that basically picture a little bit what we were saying about the low data rate. So I think, get back over the overall view on the presentation. High data rate networks, low data rate networks. I think I've shown now that from a technology perspective, all those things can be built. We actually can build very low power nodes. We can build high performance wireless nodes. So the idea of ubiquitous wireless and basically wireless everywhere clearly is a feasible style of paradigm. So let us kind of think a little bit further about some of the other challenges that I've addressed early on. Portability and configurability. And that's the last, about half an hour left. That's what the last half hour of this tutorial is basically going to be dedicated to. So it brings us back to the home environment. And if you think about it, the story there is pretty sad. It's actually, think about it, there's new devices coming in the consumer world, there's new devices coming out in the application space, there's new wireless interface, your cell phone is getting new wireless, all those things are happening. So new devices are coming in at a rate which is increasing. I think we see new things popping up at an ever faster rate. The standards are proliferating. More and more standards, I showed you a whole bunch of them, and I can guarantee you there will be more of them in the future. If you believe in a unified standard of everything, it will never happen. So standards will proliferate, both from a connectivity perspective, from an interconnect, from a recording, playback, display, all those things will vary over time. So devices do not necessarily, this is actually an understatement, devices do not interconnect easily. I think basically the house to me looks like a Tower of Babel. So that's a challenge. So what do people do? How has the industry reacted? There's a couple of ways of doing this thing. The first one is this one. This is the back end of a Yamaha AV player, one of the top end players. What they basically decided to say, we're going to support every standard. You want to have optical, we provide some optical interfaces. You have composite video, we'll provide a composite video for every channel, and so on and so forth. And you keep on adding on. So the same thing is going to happen in the wireless space. Think about what your cellular providers now starting to do. You say, well, the cell phone, well, yeah, obviously you have to have 4 bands, right? And then you add Bluetooth. And wouldn't it be nice to have 8.11 on the thing? And so on and so forth. So every time a new standard emerges, they add one more onto it. So it's the cover your bases type of strategy. The problem with this is that, first of all, it's not very attractive for lightweight devices. Small mobile devices having n different standards implemented on this type of thing, not a good idea. And it's clearly not scalable, it's not extendable into the future, and it's not upgradable. So you have a challenge here. So this is the way the industry operates today, but I don't believe it basically helps in terms of the future. The other approach is saying, buy everything from one single company. I call it the stovepipe solution, and obviously companies love this. You talk to Sony, and they really like to have you basically buy the whole stack from them, from the top to the bottom. Basically lock yourself into their particular standard sets. The way the video is encoded, the way you play it back, all the way to basically the interfaces, how they connect the devices together, and so on, so for the physical layer. Stovepipe solutions. For instance, an example of that is a HAVI solution, which was touted quite heavily by an industry consortium for quite a while, has gone a little bit on the wayside now, and has been replaced by something which is now called DLNA, Digital Living Network Alliance, that basically tries to provide compatibility. This was based on FireWire as the physical layer and put a bunch of layers on top of that. But you basically got stuck on that particular physical platform. So fix the complete stack and hope that the rest of the world will adopt is basically another type of strategy. But I don't think it will fly very nicely either, because you basically lock yourself in, and it basically doesn't open the door for innovation. So here's what I think is the right solution. And it's obviously, it might be controversial, but the idea is the following thing. It's just, how did we solve the problem with compatibility in the internet world, for instance? Well, did we make every computer talk every possible type of physical layer that you can have in the network space? Absolutely not. We have basically a single jack out there that basically talks TCP/IP and Ethernet, basically. That's what we basically have as an interface. And then you have a whole bunch of other devices and other type of strategies, ATM, all those kind of things out there that might be used to connect the devices together, but I don't have to worry about those things. It's hidden in the network. There's infrastructure that deals with the compatibility between the different devices at the different endpoints. And I think we should start thinking about the same thing for the home as well. So rather than making every device extremely intelligent and support every possible standard, why not put a box in the middle that's flexible enough, smart enough, and adaptive enough so that it basically can act as an intelligent router between your different devices. So the home router. And I call it basically the universal contents router. The box in the middle that allows me to seamlessly and on the fly connect any source to any destination, independent of the physical layer, link layer, or even presentation layer or application layer type of representation. So my goal would be to say, and I think we can do it, to build a box that seamlessly connects everything to anything, guaranteed, and by having that intelligence in there, we can even do better than that. And I'll show you what I mean by better than that in a second. I think it mirrors developments in the internet world as well. If you think about it, if we saw the first Ethernet deployments, how did they work? You had this big coax cable, yellow coax cable, and every computer had a card in it with a cable coming in, and you punch to that Ethernet, to that thick cable, coax cable. That's to make your connection. So every device had an intelligent component in the back end that basically helped to decide when to transmit and how to transmit. So the routing and everything, or basically the access to the channel, was determined by the end devices. Every end device in itself was basically having the intelligence. Clearly was not scalable, extendable, and so on and so forth. So what did we do? We introduced routers. We moved the intelligence from the end devices, the peripheral devices, to the core of the network. And routers are intelligent enough to sense what devices are there, what data rate they can talk, what type of protocol they talk, and so on and so forth, and adapt to that. Even better, they are upgradable. It's something that becomes invisible to you as a user. And they make sure that your computer, when you plug it in, it connects. So same idea, I think, should be applicable to the home as well. But there, I want to go one step further, because it's not just link layer and physical layer stuff that I'm basically concerned about, because those devices I'm going to get are also having different standards at the media, representation layer, application layer, and so on and so forth. So let me show you a very simple example. I would like to have my cell phone, which has a Bluetooth. Most cell phones come with a Bluetooth these days, so I have a wireless link in there. I make a picture with it. I would like to transmit it to a display, wireless display that has an 8 to 11 interface. Most probably, there's a good chance that the media or the media encoders that I have or decoders are going to be different. Your LCD display probably going to have some MPEG-4 type of 8064 type of interface on it. While from the cell phone, actually, I would like to have a encoder which is very cheap from a power perspective, a very simple encoder. MPEG-4 is just the opposite. It's a very complex encoder. So trying to connect those two together seamlessly is a hard problem. They're basically incompatible. But if I put this box in the middle, what I can do is on one side have basically Bluetooth protocol stack, then do a transcoding from this Prism, this lightweight protocol to MPEG-4, and then transmit it out to 8 to 11 in that particular box. So this is what we call the universal contents router. Basically, on the fly allows you to download the physical protocols. It's very flexible, very programmable, not only for the physical layer, but also for the media transcoding and so on and so forth. And once you have that, you can actually do even better things. Here's an example of one of my dream applications. Is, hey, rather than having those two very expensive speakers in my home, which are, if I position myself perfectly, I'm going to have good sound, or 4 or 6, whatever it is. Why not put 100? Everywhere around, very cheap speakers, make them wirelessly connected. Since I have a sensor network, or since I have a way of determining where I am, and since I can basically have some cleverness in my box, I can do some channel sounding, I actually can figure out the acoustics of my room, I think I can do on-the-fly virtual surround sound every place where I go. So you add signal processing into the network as well. Complex type thing that basically carefully steers the beams to the different speakers based on your location. So you add a lot of computational complexity on top of that. So that's the idea of this universal contents router. It's really something that allows you to have a set of interfaces in a flexible fashion and basically process a variety of real-time, high data rate streams from physical interface through protocol stack and signal processing in a fully programmable and upgradable fashion at extremely constrained cost and power budget. Now, here's a nice challenge for your programmable processing type of space. We're talking about, my numbers here would be a machine that basically has to 10 watt of power. I don't want to have a fan on those things. Fans are very annoying when you play audio. So no fan, so 10 watts is a good number. Cost of those box should be about $300 bucks. So it's like your set-up box or something like that, $300 to $400. However, you look at the computational requirement of this thing, we're talking many teraops of computation, because you really have to have flexible interface at all layers of the overall stack, programmable. So is it going to be multi-core? Is it going to be configurable? What it's going to be is an interesting challenge, very interesting challenge from an architectural design perspective. And this is what Hot Chips, I think, is looking at in one of the focuses of this conference. So good challenge to basically build a box like this. Just an example here of how this can work. And actually, you might say, hey, is Microsoft not doing the same thing with their media station, or is the Xbox or is the PlayStation 3 not going to do similar type of functionality? And in a sense, yes. But I think actually coming out from the perspective that this thing is a router, and not a processor, or a media processor, I think is setting your mindset. Basically looking at this as, I have a stream of data coming in, and while it's processing through the different thing, I'm going to basically do a set of operation to it. Creates a different perspective on how you build the architecture, and how you basically build the different abstraction layers of how you manage a component like this. So for instance, here I have a set of computational component elements, which could be, as I said, configurable or multi-core or whatever it is. Some of them might implement file layer, might be optimized for OFDM-like things, like we saw for different wireless standards, or basically link layer, MAC layer type protocols, which more typical processors, and then some application layers, which are your transcoders, MPEGs, where you have the motion, estimation, all this kind of complex type of functionality we do. So depending upon the scenario we're going after, we might basically flip in different components. Transcoders, physical interfaces, and so on and so forth. Like if I want to see a movie stream, I just basically say I have somewhere a media player from a Bluetooth PDA or something like that, connected to my computer. Fairly simple. I basically swap in my file layer, a link layer, connect the two together. Quite straightforward. However, if I want to do a movie and at the same time watch somebody ringing my door and do picture-in-picture, I have to go a higher level in the stack. And I have to basically swap in both physical layer, link layer, and application layer components that combine those different streams together, do picture-in-picture on the fly, and send it to that single display we're talking about. So very flexible, very configurable type of components. So what are the properties we're looking at? Durable. If you look at it, we basically replace peripheral devices very rapidly. We buy a new iPod every time there's a new version, new color out. Cell phones we replace every year or so and so forth. So those things are almost throwaway devices. But if you think about infrastructure, that's something we don't replace that often. Or a wireless router in the home, you buy it and you typically leave it in there for 3, 4, 5 years. A box like that, to me, should basically be there for 10 years, approximately. You don't want to upgrade these things or basically replace every year or so. So what it requires is flexible physical connectivity and legacy support. You have to be able to support standards of the past. Flexible link, transport, and presentation protocols. Flexible and dynamic routing capabilities. And discovery mechanism for new device and protocols. That's really what we basically this thing can do. And now, as I said, obviously, flexibility is nice. It's an absolutely essential type of thing, but it costs you a lot of power. So we have to look at architecture that basically combine power efficiency with flexibility to be able to enable this. And by the way, coming back to our cognitive radio perspective, remember the cognitive story I was talking about a little bit? So I don't believe that every mobile device, that making a mobile device a cognitive radio is a good idea. Something that sits there and scans out everybody who's around there. That's too expensive. However, actually putting cognitive capabilities in something which is infrastructure makes a lot more sense. If I have that box there, that box can easily scan around and figure out what is basically being used in terms of spectrum in your house at a particular point in time, and basically instruct the mobiles, basically have dumb mobiles talking to this intelligent type of central infrastructure component. So there's another argument why infrastructure for the home, wireless infrastructure for the home, makes a lot of sense. So this is basically a continuity of basically just what I said. Basically, actually combining cognitive with basically this universal content radio makes perfect sense. It's not cheap, and I just want to show you that it's not cheap. For instance, if you look about a 3G generation radio, it's about a 100,000 MIPS type of computation if you want to basically. If you think about some of those OFDM, of this 802.11n type things, we're talking easily things that also are approaching about a teraops. So my overall number, if I want to basically transmit or basically process 5 to 10 media streams simultaneously on a box like this, in a flexible fashion, we have to think about 5 to 10 teraops of computation or computational elements. That's kind of the numbers you have to be after for 10 watts. So interesting challenge. But again, I believe that technology scaling and clever architecture design will help us to get there. So your choice. I think there's a lot of things happening in there that basically leading to this. It's either multi-core, it is basically configurable, on-the-fly type things, whatever your particular choice is. There is a number of interesting architectures that might help us to get there. I'm not sure, actually, the question is how to develop such a thing before those chips are there, or before the technology is there. So what we did in Berkeley to start experimenting with this type of environment and this type of ideas is we actually say, well, obviously I cannot build the chips today, and we don't really know what all the applications are going to be yet, what the requirements are. Can we start building a prototype? And that's definitely feasible. Over the years, we have developed a system which is called B. B is a board, it's a large board, which contains some of the, at that point in time, top-end FPGAs from Xilinx. There's actually 5 Vertex 2 Pro FPGAs on this board. Lots of connectivity between those chips. Serial links, 10 gigabit per second serial link, optical I/O, whatever it is, a lot of interface capability, and so on and so forth. One of those boards gives us about 2 teraops overall computational capability. If you put a rack of these things together, about 5 to 10 boards, I get about 40 teraops. I think for me that's approximately sufficient now to do a lot of the goals that I've been describing about. Obviously it's not 10 watt. This is hundreds of watts of power dissipation. So we're quite a bit away from where we want to be. Then by having all those interfaces, I can plug in different radio standards, different RF front ends, wideband front ends, ultra-wideband front ends, and so on and so forth. And it starts allowing me to build this box today and experiment with it, start building my test benches, and start actually trying to understand what it takes to basically build this configurable, flexible type of architectures. There's actually a project that's going on together with a number of people, some of them are in the room here, Christos Kazarakis, Dave Patterson, and so on and so forth, to actually think about how to program those devices as well. And this allowed us actually to build some of the prototypes. By using off-the-shelf components, you take 8 to 1110 components, you take ultra-wideband components, and so on and so forth, we actually start cobbling together a first-order generation of those things, where we actually have a number of end devices with displays, audio playback, and so on and so forth. And the B itself, 5 FPGAs, is kind of the universal context router. One of the FPGAs is used as a control processor, and then we can swap in different media transcoders, different wireless interfaces into the other FPGAs based on the needs and the discovery requirements. So that's the way I think. It's at least obviously highly controversial. Every time I raise this thing up, there's a whole bunch of arguments to be made for and against it, but I believe that infrastructure can help us to basically create that portability and connectivity, seamless connectivity kind of component. So I have about 15 minutes left. What I like to do is address, to me, the most important problem of the whole thing is basically the usability of a system like this. It's nice to have all those components with all those functionalities and very complex scenarios. If you look at the DLNA website, the Digital Living Network Alliance website, they have a whole bunch of scenarios that can happen in the home, how the different devices have to interplay with each other, and so on and so forth. So it's kind of nice to think about all this type of thing, but ultimately we'll have to be able to deploy systems like this, as I said, in a user-friendly, zero configuration, zero management type of mode. That's really what you're going to go after. Otherwise, adaptability in the general consumer public is going to be 0. Think about what you have to do today. If you look at your media system at the home today, this is what it looks like. You have a whole stack of remote control devices. So what you're really doing is the following thing. You become a human router. You say, well, gee, I'm going to put a DVD in this player here. Then I want to make sure that this DVD plays to my AV player. So I'm going to put the AV player in DVD mode. And by the way, I'm going to be in the living room, so I'm going to route my signals to the living room. So I'm setting out the paths. I'm routing the signals basically manually. Then I'm going to program every one of the devices individually. I'm going to start programming the DVD player to play. The AV player has to be in rock mode or whatever it is. And my speakers typically don't have that many modes. But you basically program every one of those devices individually as well. So it's device-oriented, not function-oriented, and it's connection-oriented. What I really would like to do is something a lot more intuitive. And obviously, people are realizing that. I mentioned DLNA is an effort by the industry to think about compatibility between devices and providing some higher-level interfaces. Javi was an example like that as well. Another example, for instance, is the Microsoft Media Center. I'm not sure if any one of you has played with this. It's basically a PC-centric type of perspective. You basically take a PC, you add a set of boards to it, and now your PC is aware of the contents you can play, and it actually allows you to program what goes where. You basically pick your TV, you can pick your different channels, send it out, and so on and so forth. Nice user interface to basically deal with it, but centralized on your computer. It requires that you're basically sitting behind your computer to basically operate this type of things. So this user is still the system and the configuration manager. Still the same thing. You basically manage, you say, I'm going to do that and that and that. Not intuitive. And it's still centralized, static, and not spatially aware. It's not aware of where you are, basically, or where people are. What I really would like to do is the following thing. I would like to give a command, but I really want to say, play music. I want to hear the Beatles, this particular song. That's contents definition. And I want to hear it right here where I am, in this room, and give me the best possible quality, depending upon the I/O devices that have surround me. What speakers do I have? What source of contents do I have? And so on and so forth. That's the application level we're talking about. Really, the solution to the operability problem, or basically the use of problem, is like everything, right? If every time you have to deal with something very complex, the only way to deal with it is by changing the abstraction level. Go to higher abstractions. Hide away the layers below that. That's the only thing that can work. A top-down vision. And I think that's absolutely essential if we want to make the home of the future work. We have to start thinking about abstraction levels which are way higher than what we think about today. We should basically be agnostic of the physical layers, the devices we have around us, and so on and so forth. And what we want to think about is contents and quality of service. So, independent of network architecture and hardware platform, enabling dynamic deployment, mobility, interoperability, and innovation. That's really what we're looking at. And the way to do that is basically to layer on top of this set of devices we have, this physical platform we have, with this middleware. What you want to put on top of that is a set of services. A set of services that basically help us to interpret this very high level, location-dependent, spatial-aware type of commands that I want to basically inject. I call it the ZUMA concept. ZUMA stands for Zero Configuration, Universal, means that any device plays, multi-user optimal. Obviously, when I have an environment like that, people are going to basically trying to vie for the same resources. So you have to do resource management and optimize over the set of users in the system, and it has to be adaptive to changes in the environment. People coming in, moving out, devices coming in, devices moving out. A lot of challenges with this. Interesting, high-level challenges. But again, that's what we're talking about, opportunities for research. Resource management. Obviously now when you have a set of tasks that I want, high-level tasks that I want to map onto this set of capabilities that I have, the end device, input devices, wireless channels, data channels that I have available to me. These are all limited. I have to map those things in such a way that I basically have the maximum quality of service for my set of users. The other thing is you have to make sure that you have arbitration, allocation, things like that. It has to have a multimodal interface. It has to decouple the user interface from the functionality you're trying to perform. User interface and control point should not be connected to each other. It should be personalizable. The user is first-class citizen. So when I walk into my home, I have a certain set of privileges. I can change the security system. When you walk into my home, you should not be able to set the security settings. So basically, the idea of personalization of identities, personae, is a very important element of this overall picture. Interoperability, I already mentioned that. We should discover the new devices come in, integrate them, and utilize them whenever we can, given the commands we have, and adapt to change the environment when I walk in and out, new devices come in. And there's other things like spatial awareness, rights management, wireless spectrum usage, all this type of thing play as well. So here's kind of what we project that might play in this space. What you think about is that you have to have, from a top-level perspective, this mapping. So what you have is, I start a certain application, which would be watching a movie or controlling my the home environment, basically cooling, heating, looking at my energy usage, and so on and so forth. These are the set of applications we have. Those applications and how they're going to be run is going to be determined by what I call the environment I'm playing into. It's an abstract vision of the home environment as it stands. And what are the components of such an environment? Three elemental type of things. Number one is content. What do I have available in terms of media content? Which could be huge. It's what I have on my cell phone. I have a set of pictures there. It could be what I have on my disk. It's what I have available through the internet, and so on and so forth. So a list of contents that's available to me at this point in time, under certain conditions. Capabilities are determined by the physical environment I'm in. If I'm in this room, I have this type of display, I have this type of speakers, this is sensors that are available to me, and so on and so forth. So this is the abstraction of the physical world that I'm operating in. And then finally, to basically connect the two together, you have the personae, or the users, which basically set their preferences, access modes, and so on and so forth. So given the environment then, the whole idea of this higher level interface is to take an application, whatever application is, and dynamically map it onto this environment given these constraints of contents, capabilities, and personae. That's really what we're talking about. So what I do is I call it the ambient operating system. It's a distributed operating system that basically helps me to run that home environment given basically a set of flexible resources. So rather than management of change, today most of that stuff is going to be sitting in the algorithms. The higher level application has to take care, oh, a new device pops up, that's what I should do. No, a much better approach is to provide this as a service. Management of change, the idea of what the capabilities are, what the personae are, and what is a service that is provided by the system in itself. Potentially running on those UCR, this Universal Contents Router. So this is the ambient intelligent playground. It's a playground combining multiple available media and data contents, capabilities of the IT environment, and the preference of the privileges of the user present. So I have contents, capabilities, and people. And what we try to do is dynamically map your application onto your platform based on the constraints given by those three elements. I have a set of other slides on this, on how to do this exactly. Bottom line, it basically comes down to a set of services. But once you're basically there, life can become a lot more intuitive and flexible. And we don't really have to understand anymore what the physical capabilities of the systems are. Let's jump me, for the sake of time, let me jump through those slides, give some time for questions. So here's an example, for instance. I have an application that's running. An application consists of a set of tasks. For instance, I'm watching my home theater. I'm a home theater application, which allows me to have a movie to play to a renderer to one particular TV set. And the renderer could run anywhere, could be running on the TV set, but could run in the intermediate box as well. Obviously, while I'm running my TV set, my movie, I want to basically control the lights. So that's an integrated part of the thing. When the movie starts, you dim the lights. And there's some control points that basically allow me to stop, start, whatever it is. So that's application one. I have a second application, which is my security system, which is a video camera mounted in front of your front door that basically, once a user is detected, it's a sensor, motion sensor, it turns on the video camera, sends live video camera, and sends out a video stream. Presumably, I would like to see that video stream popping up on the same screen where I'm watching my movie as a picture-in-picture. So these are a set of tasks, and initially, this might be mapped initially on a set of devices. This might be mapped on another set of devices. But in order to basically make it work together, what I have to do is dynamically bring those tasks together, look at the capabilities of what my devices have, and either do merge them together by basically putting the picture-in-picture component in between the two and run it either on the remote, on the television set when I have that capability, or run it on the universal contents router when my TV set doesn't have that capability. So what it basically means is on the fly taking those tasks together and map them onto the environment and its capabilities in a dynamic fashion. So where are we this? Well, actually, we have a prototype system running on this where you actually can have a set of those tasks. You will have a capability of discovering devices when they enter the room, what their capabilities are, and have actually this dynamic mapping capabilities and a set of demos that do exactly that. So first order prototype, a lot of stuff to be done still, but it shows that it is possible to raise the abstraction level substantially and make this home, very complex home environment, a lot easier to use. So summary. I think the future of wireless infrastructure is really in the seamless connection of this myriad of emerging mobile, multimedia, and sensor devices. And I think the home is an ideal playground for that. There's other ones like the car, the office, other ones, and so on and so forth, but I think the home is basically one where a lot of the interesting things can basically happen. And that's why we picked it as the first one to play at. The other thing is I believe that we should start thinking about infrastructure. We have thought about infrastructure for the wireless, for the internet. We have talked about infrastructure for the cellular network. Why not think about infrastructure for the home? Something that allows us to make interconnection between devices a lot easier. To make it really happen, I think we have to change some paradigms in the way we use devices, connect devices, but also how we think about it by usage pattern. And I think top-down vision with raised levels of abstraction is absolutely essential. And finally, I think that multimedia networks and wireless sensor networks are basically having a symbiotic relationship. Putting the two together really can create something which is new and exciting, and potentially will lead to applications we cannot even think about today. So thank you for your attention. We have room for some questions.
Hi, Henry Baker. The question is actually for both of your parts about the RF, both the high power and the low power. The power, of course, goes down dramatically if you can actually aim and get very high gain between the transmitter and the receiver. I mean, here's a good example right here. I mean, you can see that. It's 1 milliwatt. Is there any way of taking advantage of very, very high gain antennas, for getting your low power transmission?
Good question. Absolutely. If I basically can direct energy, it's basically spatial diversity. What I'm doing, instead of basically broadcasting to everyone around me, I basically direct my signal to basically the intended point. For the high data rate application, I believe that this is an absolute right thing to do. If I have multiple antennas to start with on my devices, as well as my my infrastructure component, actually trying to beam the signal in the direction of the device you have basically will help you to basically increase spectral efficiency quite substantially. And again, this is where infrastructure will help. It's easier to do this on a base station than on a mobile. Okay? So I believe that the UCR concept and basically directional transmission work perfectly well. For the sensor network space, it's a little bit harder. Actually, in order to basically make directionality, again, I need multiple antennas. And today, already, if you look at the node here, this little cube node that I showed you, actually getting a single antenna at 2.4 gig on this type of things is very hard. Trying to put multiple antennas with basically allow me to do beam steering and so on and so forth on a thing like that is very hard. So there I believe that actually rather than using a single beam steering type of thing from node to node, actually having multiple nodes collaborating with each other and using short distances of transmission and multi-hop on top of that might be the better way for the low power, low data rate type of application. And it's mostly determined by size. So, but absolutely right. If I can do beamforming, for instance, for my speaker application, it's a perfect example, right? I have my base station, I have a set of speakers. Why not beam it target? I know where the speakers are, I beam the signal right at it, rather than basically having to basically broadcast to every one of them.
The other comment is that most electronics already are pretty good, at least radio transmitters. In fact, we have to shield them to keep them from. Anyway, you could take advantage of just the existing.
Yeah, it's a good question. Can I basically use EM as a way for me to transmit information? I've been thinking about that, actually. I said, maybe why not jitter the clock of my microprocessor to transmit some information over it? Interesting idea. Not sure how it basically plays with, but yes, they're definitely transmitters. And if I can basically supermodulate some information on top of that, would be an interesting mindset. However, it challenges a little bit the designers on the other side. I don't think the Intel crowd is going to be very happy. I say, I'm going to basically start modulating your clock.
Yeah, in fact, my question was similar, that in scavenging, you didn't mention radio as a source of power. And also, the thought comes to mind that a lot of this is also very reminiscent of RFID and the research they're doing there. And I noticed you left that out, and I'm wondering, is there a reason why you didn't bring that into the very creative fray that you're developing?
Very good point. Obviously, RFID is definitely a player in this space. I didn't go into it because obviously time limitation, but obviously it plays a big role. Now, RFID is indeed an average scavenger, right? All the power comes from the receiver. The receiver transmits the power, you backscatter it, you send it back. It has some advantage, obviously, that the transmitter is basically very low power. It can be zero power because it can get all the power from the receiver. Some limitations, very important limitations, obviously, is that power rolls off as R squared. So it works really well for distances which are quite small. If the distance gets larger than that, the power that has to go to the transmitter
to the receiver, it becomes larger and larger and larger. So you have to throw a lot of power at it to get the signal back. It's an asymmetrical situation. So if I have the capability of having a node which is plugged in on one side and a mobile node on the other side, then obviously RFID makes perfect sense. So to be honest, I'm actually playing around quite a bit with this type of what I call asymmetrical passive receivers for some applications, not particularly in the home, but let's say in automotive applications, smart tires and things like that. The idea of actually beaming power at it to interrogate a set of sensors that are embedded in the tire is something we're playing around with. And it's very attractive, absolutely. So it is part of the game. But remember, typically RFID tags as they come today are pretty dumb units. Making more clever or hybrid structures could be quite attractive. Yes?
Lazar BWRC from Connex Technology. In your example for the router, home router, you mentioned some estimates of terabytes, of teraops, and some power. Would you elaborate a little more of where these estimates come from?
Yeah, I can go into detail on this. The real challenge is not in the transcoding. You know, transcoder, we know what the numbers are. We can do H.264 transcoder and things like that. The numbers there are not too bad. The real numbers really come from the physical interface. If I basically start doing flexible physical interfaces, basically your FFTs, the IFFTs, and all this type of things I need for the OFDM type things, the correlators I need for spectrum and so on and so forth, that's really where the numbers come from. These are operations which are not very complex. They're not 64-bit floating point. They're basically limited length, word length type of thing, but huge number of computations to be performed. So this speaks for some heterogeneous architecture. I think for the front ends, typically I'm happy with narrow data paths, while the more I go to the back end, let's say when I start doing image coding and so on and so forth, there I probably want to go to larger word lengths type of things. But the majority of it, I showed you some numbers with the 3G type thing. You go to some of the other things, the numbers really stagger up if you go to a more flexible software-defined type of radio front end.
Yeah, there's, I mean, some of the presentations that will be in this conference later, there are some of the devices go to half a terabyte, half a teraop. So you're saying those will be challenging to perform in that environment.
That's right, exactly. So think about it. You take those chipsets that are out there. Now you think about a fully flexible implementation, and you think about 10 HDTV streams at the same time. That's kind of the numbers that we're basically starting out.
That'll be interesting continuing talking to you with that.
Okay.
Thank you.
John Massey from TechVisor. You said you weren't going to talk about security and privacy, but could you say a few words about that? The reason is I have this nightmare that I wake up one day and find that my microwave has sold Viagra to my fridge and my stereo.
Yeah, absolutely. And this is something I hear every time I give this presentation. Somebody is going to say, "Gee, I'm really worried about this." So there's a couple of variety of things that are basically involved in this. And you can put them in different categories. On one side, it is obviously the privacy issues. Absolutely important. You basically want to make sure that your neighbor cannot start controlling your heating system, for instance, in your home, which could be happening. Now, the question is, with everything which is secured is, how much do you want to pay for it? Right? It's, what is it worth to you? If I can make sensor networks very reliable, very private, and so on and so forth, at a cost. And some of the information I care about protecting, some of it I don't. And that's really what we have to decide on is, what are the levels of protection? Again, it becomes easier when I start doing this at a higher level. Do I do this end-to-end? Can I do this in the middle box? And so on and so forth. Interesting question. The community at large has only recently started to address those things in a reasonable fashion. And there's some interesting things that have emerged over the last 2-3 years in this space that I think are very promising. So there's work going on in that space. But you're totally right. There's some very interesting side effects that might come in. I was once on a panel, listened to a panel where they had a set of lawyers talking about this. Social aspects and so on and so forth. For instance, the question is, if I have a sensor network in my home and I record data, could this be used in a court type case later on against you? And there's some precedents. turns out, for instance, there was one case that they convicted somebody by monitoring or basically looking at his or her energy bills. It was a case of growing marijuana in a home. So they figured out at a certain period of time, basically energy usage of the home basically went up dramatically, and so there was a correlation between this and the plants being growing. So that was allowable in court because energy bills are considered basically public information. However, if I can now snoop on the sensor network and detect how many people are in the home at the same time. This was another case that basically people use information like that to detect that it was a divorce case. There were more than a single person in the home at a given point in time, at a given time. So that information was basically ruled not to be not accessible in court because this is private information. So there's very interesting legal type of aspects to this thing as well as how the information can be accessed and so on and so forth. The other part of the security part, which worries me also very much, is what has happened in the media industry and the trends in the media industry, the whole DRMF type of thing. I mentioned this briefly, digital rights management. The way it's done right now, under the push of obviously the media and the IP right companies, is that they basically have now end-to-end encryption. They basically encrypt the source, and it's a link level type of approach. It doesn't allow you transcoding. It doesn't allow simple routing of the data. It doesn't allow you to go from one place to the other one in a flexible fashion. Big challenge, and DRMF could kill this whole idea. I actually had a discussion with the vice president of Sony a year ago about exactly this topic, the guy who was in charge of DRMF, and he fully admitted this. Yeah, absolutely, we know that, but it's the only thing we can do today. However, if we can come up with a better proposal of how we can do management of IP in an environment like this and guarantee the rights of the user, then obviously we can make some breakthroughs and new things might emerge. So I think there's work to be done, but we really have to come up with alternative situations or we're going to be stuck.
So let's make this the last question.
Yes.
Yes. Most appliances in a home are wired on the power line, and even a speaker requires a lot of power to drive it. Wouldn't power line network make more sense than a wireless network?
Yeah. So obviously I put a little spin on it. I like wireless. I'm from the wireless center. But it's clear that a network like this is going to be heterogeneous. If something is plugged in the wall and I have basically signal transmission capabilities over that power cable, so be it. I'm going to use it, right? So number of devices obviously can be addressed that particular way. However, be aware that other devices are not going to be. If you want to have things that are mobility, things that come in and so on and so forth, they're going to be wireless. And so it's going to be a nice mixture of the two. It's a heterogeneous environment. Now, my UCR approach, the Universal Contents Router, basically doesn't say anything about that. I can have wired interfaces into that. I can connect to your X10 network. I connect to any network that's basically in there if I can transcode the protocols between each other. Rather than having to do what I have to do today, if I, for instance, want to control my AV player using my X10, what I have to do is first, after the power cable, I put a little infrared booster out between the two, send the signal, translate the power signal into an IR signal that basically is interpretable by my AV box. I think we can do way better than that if you basically have that infrastructure in place.
This is a business perspective question. So you, in one slide, you separated two things. One was the multimedia networks, and the other was the sensor networks. So from a business point of view, it seems to me that there's not a lot of money or very little money can be made from the sensor networks, people who are in that space, but a lot of money can be made on the multimedia. Is that correct? Can you?
I think at this point in time, you're absolutely correct. And the sensor network space today, projection, is going to be, what is it? The numbers are pretty dismal in terms of overall business projection by the year 2010. We're talking about a business which is potentially a couple of $1 billion or something like that. It's not huge. However, the potential is enormous. I think wireless sensor networks will grow substantially, not only for the home, but for basically automotive, industrial control, environmental monitoring, and so on and so forth. But you're right, from an overall business perspective, this is if you're a semiconductor company, it's a tough sell. It has to be sponsored one way or another. I've had actually discussions with CTOs until I have a number of semiconductor companies about exactly that. Say, gee, if I basically have your little wire sensor node, it's 4 millimeters square. I make one wafer, 12-inch wafer, I get about 200,000 components out of that. So if I basically make 10 wafers, I have basically supply everything you need for a whole year. It's a challenge, absolutely. But at the same time, as I pointed out already, the impact that those things can have in terms of cost reduction, just look at the energy and home environment management and so on and so forth. Actually subsidizing those things makes perfect sense. It pays back. And so you shouldn't look at the cost of the semiconductor component itself. I think actually the services that are delivered by that are easily going to pay for the cost of the electronics development.